So good morning. Welcome everybody to this session. Essentially, we will have two groups of talks. The first one will be focused on the study of the chaotic nuclei, while in the second part we will see some future perspective about some experimental activities at JLab and at JPark. So let me introduce the first speaker, Professor Tetsuo Hyodo from the Tokyo Metropolitan University, and he will speak about the theory of the few-body chaos nuclear systems.
Okay, good morning. This is Tetsuo Hyodo speaking from Tokyo Metropolitan University. And today I'd like to talk about the few-body chaotic nuclear system from the viewpoint of the theoretical activities. Let me first thank the organizers, in particular, Ilji Maresh, for kind invitation. Although from the online presentation, I try to deliver you some recent topics on the chaotic nuclear physics. So here are the contents of my talk today. I will first focus on the description of the lambda 1405 and also the chaonucleon potential that will be later on applied to the few-body chaotic nuclear systems like chaotic nuclei and also the chaotic deuterium, and then summarize this talk. So recently I wrote two review articles. One is done together with Masayuki Niyama, basically focusing on the strength baryon resonances. And for the chaonucleon systems, I wrote an article together with Wolfram Weise, which covers not only the few-body systems, but also the many-body systems of the chaos nuclei. So if you are interested in, please visit these references. So let me go on to the first part. So lambda 1405, I think I don't need to explain to very much detail, but as you may know, this particle is known as an exceptional state in the conventional Koch model picture. The celebrated Isuga-Kar Koch model can describe well the negative parity baryon excited state except for the lambda 1405. And this indicates that this lambda 1405 has an exotic internal structure in addition to this three-core component. And what is missing in this simple three-core picture is the coupling to the meson baryon states, because the lambda 1405 actually decays into pi sigma at a lower energy, and it exists very close to the chaonucleon threshold, meaning that this system should be treated as coupled channels meson baryon scattering, like a k bar n pi sigma systems, and we have to deal with this meson baryon coupled channels scattering amplitude from theoretical viewpoint. So here's a list of the experimental data that can be used to constrain the meson baryon interactions. So above the k minus p threshold, we have the k minus p total cross-section data, which has been accumulated by old bubble chamber experiment. And also on top of this k minus threshold, we have the threshold branching ratios, and also the measurement of the chaotic hydrogen give us a very accurate determination of the k minus proton scattering length. I will say that these three categories of the experimental data are the direct constraints on the meson baryon scattering amplitude, because there's one-to-one correspondence between the experimentally observed quantity to the meson baryon scattering amplitude. But on the first day, as Eulogio mentioned, this lambda 1405 energy region is only accessible through the coupled channels of pi sigma, because this is the substrate region from the k bar n. So this information on this channel, namely the pi sigma invariant mass spectrum observed by photoproduction experiments like Rex and Klaas, and also the proton-proton collision by Hades or k minus deuterium reaction on the JPark experiment, is very much important for the description of the lambda 1405. However, I would say that to relate the experimental spectrum to the meson baryon scattering amplitude, we need additional theoretical input, namely the reaction model that, for instance, are chiefly discussed on the first day to construct the gamma p going to meson baryon state. That part also requires some theoretical argument. So in order to avoid such the ambiguity in the theoretical model on the reaction part, in our study, which has been done in collaboration with Yoichi Ikeda and Wolfram Weise, we just try to use this direct constraints, namely the threshold branch k minus p experimental data, to constrain the meson baryon scattering amplitude and try to look for the its consequence-wise substrate extrapolation to study the structure of the lambda 1405. So here's a comparison with the experimental data with the this theoretical amplitude. So here you see that K minus proton total cross-section data is well described. This is the elastic channel, these are the inelastic channels, and threshold branching ratios, and also the ionic hydrogen shift and width are also well described here. You can see the accurate description of the all existing data is achieved with the chi-square over degrees of freedom is almost unity in this fitting. So once we obtain the theoretical amplitude nicely, we can now try to analytically continue this scattering amplitude into the complex energy plane to look for the pole of the resonance. So these are the results here. I plot with the black symbol the result of our pole position in the complex energy plane. This is the real axis. This is imaginary. Divine threshold here, pi sigma threshold here. So we found two poles of the lambda 1405, as already discussed as a two-pole structure of the lambda 1405. And not only in our analysis, but also with some additional studies by Guo and Weil, or Mai and Meissner in the independently. And also in their cases, they also utilize the pi sigma invariant mass spectrum in their own way to constrain the theoretical data, theoretical amplitude, and found basically the similar result, namely there exists two poles in this energy region, summarized in this figure. So according to these activities from the 2020 edition of the particle data group, this lower energy pole is now called a new baryon resonance, lambda 1380 with 1/2 minus. And the name of this lambda 1405 is now reserved for this so-called higher energy pole, which is not at the nominal position of the 1405, but much closer to the nucleon threshold. And of course, this lower energy pole still has large ambiguity in the position of the pole, namely the eigenenergy. So in the future experiment or future theoretical studies, it is very desirable to pin down the exact position of this lower energy pole, or the position of the lambda 1380 resonance. So once you can construct a meson baryon scattering amplitude, it would be great if this result is applied to, for instance, the ionic Fibonacci systems, and also the correlation function that has been intensively discussed yesterday. And for that purpose, the on-shell scattering amplitude itself is not very useful directly to the application for this nuclear and deuterium. And for that purpose, it is desirable to have a kind of local K-baryon potential that can be easily implemented to the calculation of the Fibonacci systems, because we have established the Fibonacci technique to calculate rigorously for the Fibonacci Schrödinger equation. So in this paper, we have presented the theoretical framework to construct an equivalent local potential that describes the scattering amplitude of chiral SU3 dynamics. And using this framework to consider the constraint, a new scattering amplitude, we have constructed two kinds of potentials. One is a Kyoto K-baryon potential. This is a single channel version, namely the effect of the lower energy pi sigma and pi lambda are renormalized into the imaginary part of this potential. This has been done by Kenta Miyahara, my former student, when I was in Kyoto. And a couple of the channels version is also constructed in collaboration also with Wolfram, where the explicit treatment of the pi sigma and pi lambda channels allows us to use the real and milder energy dependent potential of this coupled channel system. And once you construct these potentials, then you can directly apply these potentials to study the Fibonacci system and also the correlation functions. Let me show one result from this potential. So here plotted the value of the potential on top of the lambda 1405 pole. Here the R is the relative distance between K and K1 and the nucleon. And the real part is negative, meaning that this is an attractive potential. and has some small imaginary part representing the decay or absorption into the pi sigma and pi lambda channels. By solving the Schrödinger equation with this potential, you can calculate the wave function, and taking absolute value square, we obtain the density distribution of KYN system on top of the lambda 1405. And here you can see that this interaction potential is of short range because there is no pion exchange between K by N, and the density is actually distributed even above the region where the interaction potential is almost vanishing. So this suggests that the spatial size of this lambda 1405 is much larger than the ordinary hadrons, and suggesting this meson baryon molecule picture for the lambda 1405 structure. So this, I think I don't need to explain it very much detail, the correlation function, but has been intensively discussed yesterday by Kamiya-san as a talk. And also later in this session, Mona will give us more update on the, in particular, this source size dependence of the correlation function. But one thing I would like to emphasize here is that this so-called Kuhn-Pratt formula, we need the wave function of the two-body system, which can be obtained by implementing our coupled channels potential, so that we can calculate also for the correlation function. Okay. Now we come to the application to the Fibonacci system. First, we discuss chaotic nuclei and briefly mention the chaotic deuterium later on. So the simplest three-body or the chaotic nuclei is the three-body system of K bar N. And sometimes you have seen that big table with many theoretical description, theoretical prediction with the different binding energy and width. But you have to be careful on the treatment of the theoretical framework. Namely, the K-bine interaction should be as realistic as possible, and also the three-body calculation should be as rigorous as possible. Here, I mean by realistic is that this potential should fit to the experimental data, namely the K minus P cross-section and branching ratio that we have been discussing. And not only with this, the most importantly, the Siddhartha constraint of chaotic hydrogen should be implemented for the realistic interaction of the K-bine system. And as far as I know, there are only two calculations that satisfy this realistic interaction in combination with the rigorous P-body treatment. One is done by Czech group, Levy and Shevchenko, using the Faddeev equation with their own separable potential, and the others are our calculation, basically led by Wataru Horiuchi in the Hokkaido University group. So here the result, comparison of the result of these two papers. By the way, before going to the three-body, let me explain their separable potential developed mainly by Shevchenko. So they have a one-pole Siddhartha potential, two-pole Siddhartha potential, and also chirally motivated potentials. Now, in their, even in the one-pole hypothesis, the pole position of their lambda 1405, it appears not at the 1405 nominal position. This is again thanks to the Siddhartha constraint. So in each case, the position of the lambda 1405 appears somewhere around here. Now, by applying this potential to the three-body rigorous calculation, we obtain the binding energy and decay widths like this. And as you can see, that binding energy and widths are quantitatively somehow different from each other, depending on the employed potential. So even if we construct the realistic potential with the rigorous three-body calculation, there still remains ambiguity. This is actually true. So we have to be careful on, we have to keep in mind that this kind of ambiguity still remains on the choice of the two-body interaction. But one thing I would like to emphasize here is that these decay widths calculated in these papers are only the mesonic decay widths, where the pion existing in the final state. Okay? There is no two nucleon absorption process in this calculation, where the decay going to the lambda n or sigma n final state is not included here. So when you want to compare this result with the experimental data, for instance, JPAC-E15, where they in fact observe the signal from the lambda p final state, which is nothing but the two nucleon absorptive process, you have to be careful on the that this effect is not included in this calculation. And I would say that this two nucleon absorption not only increases this decay width, but also may change the binding energy, because you can consider the process k by n going to lambda n and coming back to k by n. that gives you the self-energy correction to the real part of the energy, meaning that binding energy can also change. So such effect, to include such effect will be the next step from theoretical viewpoint to be compared with the experimental data. So in our own free-body calculations, we not only for the three-body system, but going to the system with mass number equals 6, namely the seven-body system, using the stochastic variational calculation with the correlated Gaussian basis, mainly developed in the Niigata University group. So yeah, potential is the Kyoto K-Vine potential for Kn part, and to nucleon part, we use the AB4 prime potential. Then they obtain the result in the 3-body, 4-body, 5-body, and 7-body system like this, with this isospin and spin parity combination. Here, this 7-body system, 0 minus and 1 minus states are almost degenerated, and it depends slightly on the potential employed. So it may be interesting to see the spin parity of this system to check the dependence on the nucleon potential. And interestingly, this quasi-bound state can be observed for these systems with these quantum numbers below the lowest threshold of the, for instance, decaying to the this 4-body system appears lower than the 3-body plus nucleon threshold or something like this. And again, in this decay width, we do not include the multi-nucleon absorption, which may be important if you go to the large binding energy cases where you have more nucleons inside, and anti-kaon can have more chances to touch with several nucleons at the same time. And even without these multi-nucleon processes, sometimes the decay width can be as large as the binding energy. So we have to be careful on the interpretation of the signal, namely the very large decay width state, namely very short lifetime state, may not have the notion of the state itself. Okay? It is very fragile. So this is one thing we obtain for the nuclei. And from the theoretical viewpoint, I think it is interesting to look for the interplay between the nucleonic correlation and nucleon correlation in these systems. I can show you two examples. One is a two-nucleon system. So two-nucleon, you can combine it with the spin singlet or spin triplet. And we know that the bound state of deuteron appears in the spin triplet component, and the spin singlet is unbound, although it is very attractive and it's about to bound with the large scattering length. But the ground state of the two-nucleon system is known as the spin triplet. What happens if you put anti-kaon? The result is like this. So you obtain the 3-body quasi-bound state in the spin singlet component, while the spin triplet is unbound with respect to the decay into the nucleon and lambda 1405. The reason is as follows. Because of the fermionic nature of the two nucleons, the isospin of the two nucleon system is constrained. And because of this, the fraction of the k bar n I equal 0 pair and I equal 1 pair in this system and that system is just opposite with each other. Namely, in this case, isospin 0 is 3 times larger than isospin 1. This is, in this case, isospin 1 is 3 times larger than isospin 0. And isospin 0 component is the place where the lambda 1405 exists. Namely, this has a strong attraction. So this configuration is favorable from the viewpoint of the Kn interaction. But just by looking at the ground state spin, you see that in the absence of the anti-kaon, the ground state spins are triplet, namely spin 1, while by putting anti-kaon, this configuration is totally destroyed, and the ground state appears in the spin singlet, spin 0 state. So in this system, k-bind correlation is so strong that the nucleonic bound state is disappeared, and the quasi-bound state appears in a different channel. This is one thing in the two-nucleon system, but that's not always the case. If you go to, for instance, a 4-nucleon system with this spin parity isospin and spin third component state, where you have a 2 charge basis component. One is a 3 proton, 1 neutron, and 1 k minus, 2 proton, 2 nucleon, 2 neutron, and k0. And these in-front coefficients are determined by the dynamical 5-body calculation. But before calculating this, let me guess which component becomes dominant from the viewpoint of NN and k-bind correlation. From the k-bind correlation, as I mentioned, it is favorable to have as much as isospin 0 pair. And if you count the number of pairs, the isotindero pairs, there are 3 bonds in the first component, and there are 2 pairs in the second component. So from the viewpoint of the kaon-nucleon interaction, the first component should be dominating this wave function of this system. But if you look at the nucleon part, this TPNN system with spin 0 can be combined into the alpha particle. So this, while this is not. So from the nucleonic viewpoint, this second component should be dominant. So this is just opposite way from the K by N and NN cases. And the dynamical calculation shows us that the second component is dominant, meaning that in this particular system, the nucleonic correlation is so strong that even anti-kaon cannot destroy this alpha particle correlation. Of course, the alpha particle is known as a very strong correlation in the nuclear physics, so that can sometimes win over the K by N. So I think I just briefly mentioned the chaotic deuterium at the end. So chaotic deuterium is a system of the combination of the strong and Coulomb interaction. Basically, anti-kaon is bounded by the Coulomb interaction, which is very far away from the proton-neutron, the 1 femtometer scale. But sometimes kaon can have a small overlap with the wave function, with the proton-neutron, and at that time, we obtain some strong interaction effect in the Ko minus proton, K minus neutron. And that appears as a shift and width of the chaotic deuterium. Again, there are many theoretical calculations, but I would say that we need also rigorous three-body calculation, including strong and Coulomb force, and with the realistic K-Bahn interaction should be employed. Again, there are only 2 calculations. One is the Janos-Levi, and the other is our group. And we see that these are the results depending on different potentials. Again, which is small deviation that can be tested by the forthcoming experiment like JPAC 57 or CW2. So here's a summary. So,
the time is over.
Okay, so just I leave this summary. So yeah, thank you very much. That's all.
Thank you, Tetsuo, for this very exhaustive review. So now we have a few minutes for the question, comments from the audience. Josette?
So can you go to page 9? That your page 9. Yeah, exactly. There, when you calculate the correlation, I mean, that was discussed already. I mean, yesterday. I mean, you see, you have the other transitions. I mean, therefore, when you say core, you have intermediate states. All the intermediate states, all the K, the coupled channels, the 10 coupled channels that can go to K minus proton in the final state. So then the transitions from these states to K minus proton, you know very well. That's what your theory gives. But then you need also the input there to the left, where you have there, I mean, the wiggles. I mean, there you need, I mean, the input of the, you know, the strength of the production of these intermediate channels. I mean, where do you get this information from?
Okay, I think all of you is speaking. Thank you for the question. And well, actually, as Kamiya-san discussed, in this particular calculation, we use it as a kind of parameter, but we can have some estimate from the statistical model prediction. And later on, Ramona will talk about this system, and this so-called omega parameter can also be estimated by using some experimental technique, which what we essentially need is the relative weight of the production of the pi sigma relative to the K bar n in the beginning. So that can be estimated by some experimental technique. And that will be also intensively discussed probably with Ramona in data in this section. So please stay tuned.
Okay, we have a last question from Weise.
Hi, Tetsuo. You mentioned repeatedly that the non-pionic absorption process could be potentially important. I think it's not only potentially important, I think the whole discussion of bound or quasi-bound states depends very much on the very subtle balance between attraction and absorption. And here I mean non-pionic absorption. If one looks at the E15 experiment, usually people call that evidence for a bound state, but the width of that state is 100 MeV. And a state that lives for 10 to the minus 23 seconds or less is usually not called a bound state. So I think it is very, very important to expand this table that you just show by including the true absorption processes.
Actually, this is done in a paper by Yad and myself.
Yeah, okay, thank you for the comments. Yeah, I actually completely agree with you. So it's very important, but theoretically speaking, it's a bit difficult to treat rigorously of this process using the Q-body technique because the number of particles will change from 3 to 2. But we can make some kind of perturbative estimation, so which can also be used to see which direction this table change. So yeah, that I think very important. Thank you.
Okay, let's thank again Tetsuo. And now we move to the experimental side of the problem. So it's a pleasure to invite Dr. Takumi Yamaga from Riken.
Yes, I hope everything's fine to start my talk.
Did you share your screen?
Is it okay?
Yeah, okay. So you see the title, the Contribution Experimental Study of the K-bar NN and Future Experiments for Kaonic Nuclei. Please.
Okay, so thank you, Chairman. I want to thank all organizers for inviting me and giving me a great opportunity to talk in this conference. And as I talk about experiment search, a study of K-bar in one state, and let me start from a brief, very simple introduction because we all have already heard the nice introduction by the previous talker. And as you know, the beginning of the story is a strong attractive force given by the K-bar interaction in a spindle channel. And this strong attractive force is enough to make a K-bound state of a kaon and anti-kaon and nucleon, or anti-kaon and nuclei. And as you know, the lambda 1405 is considered to be the K-bound state of the anti-kaon and nucleon two-body system. And as a natural extension of this, a K-bound state of anti-kaon and nuclei has been considered. And many theoretical works and experimental works has been performed, especially for the K-bar K-bound state, three-body bound state, which is the lightest kaonic nucleus. And by considering the three spin-1/2 particles coupling, there are three possible configurations like this. One is made by the spin singlet NN pair with anti-kaon, which make total spin-1/2, and the other two are made by the spin triplet NN pair with anti-kaon, which make total spin-1/2 or 3/2. And by considering all particles in S wave, spin and parity of this state can be determined. That means parity of this state should be negative, and spin of this state should be the same as the NN spin. So if the NN is a spin singlet state, a spin parity of the K-bar NN will be a minus. And if the NN is a spin triplet state, the spin parity will be as a minus. And as the previous talker said, the middle one is expected to be the ground state of the K-bar NN because it has a larger K-bar N1 spin 0 component, which is 3 times larger than the spin1 component. So this is expected to be the ground state. And indeed, all of the theoretical calculations suggest that this is a ground state. And almost of all the theoretical works reported that the left one and the right one is unbound. There are many theoretical works on the K bar NN, and all of them suppose the existence of the K bar NN, but because of the large ambiguity, especially for the energy dependence of the K bar N interaction, predicted binding energy and width is much widely spread like this. So the experimental search for the K bar NN is very especially important, not to confirm not only the existence of this state, but only to determine its binding energy and width. And there are several experimental studies for the K bar NN so far, but there was no conclusive result so far. But recently we finalized our result of the JPAC E15 experiment, and we finally observed a clear signal which can be interpreted as a K bar NN signal. So today's my talk contains two parts. The first part, I will summarize the result of the JPAC E15 experiment, and second part, I will show some our future plan for systematic study of the chaotic nuclei. So the first JPAC E15 experiment. In this experiment, we choose the production reaction of the K bar NN as helium-3 K- nucleon reaction on the helium-3 target. And especially, we focus on the K- neutron reaction to produce the K bar NN state with Iz equal plus 1/2 state, which has positive charge. And we focus on its decay into the lambda p pair. The right-hand side shows the detector system of this experiment. There are three major parts: beam spectrometer and cylindrical detector system and forward spectrometer system. And by using the cylindrical detector system, we detect the decay product of the K bar NN, lambda p pair, and we perform the exclusive invariant mass spectroscopy to search for the K bar NN. To do this, we select the specific final state, lambda Pn, and then we measure the lambda p invariant mass and its momentum transfer. So at first, we select the lambda Pn event samples. Here, I show the missing mass of the lambda p detected by the CDS. And here, clear events from the signal of the lambda p in the final state is seen as the peak at the neutron mass. And we evaluated the signal ratio in the final event sample as about 80%. And there several background contaminations mainly comes from the sigma 0 Pn or sigma minus pp final state. Actually, these two final state is hardly separate completely. So about 20% of final event samples are coming from sigma 0 Pn and sigma minus pp final state. Additionally, there is a large contribution from the mesonic final state, but in the present analysis, such mesonic final state can be excluded, so its contamination is negligible. And this is obtained two-dimensional distribution on the invariant mass of the lambda p as the x-axis and the momentum transfer to the lambda p as a y-axis. And the axis is a double differential cross-section, so that we have already corrected the acceptance and efficiencies. So you can see the clear event enhancements around there. And the important energy is this, the mass threshold of the K bar NN, and left-hand side from this red line is a bound region. And clearly, one event enhancement is located in the bound region. The other two is located in unbound region, but they are on the kinematical line, this blue line, which is a kinematical line of the quasi-free reaction. So to explain the reaction processes, to contribute, we perform the spectral decomposition by introducing 3 model functions. One is a K-binary production process, or of course, whatever the resonance state production. And it has a Bragg-Wigner formula shape on the invariant mass side, and a wave Gaussian form factor on the momentum transfer side. An important feature of this process is that the peak position of the events it depends on the momentum transfer. The second component is a quasi-free process originated by the K-neutron reaction. And events of this process is located along the kinematical line of the quasi-free, which is blue line. And third is actually similar to the second one, but this is a quasi-free process originated by the K-proton reaction. And if we measure the lambda n system for this process, the similar structure as the second component will be observed. But now we measure the lambda p pair, so events of this process they widely distribute all in the whole kinematical cloud region. And by these 3 model functions, and by considering the background from the sigma 0 pn or sigma minus pp final states, whole distribution of the samples are very reduced like this. So the main discussion is what is the observed peak. And as I said, the important thing is that a peak position of this observed peak does not depend on momentum transfer, so that this should be the signal of the resonance state. And its mass position is rarely below the mass threshold of the K-binary. And another important thing is that we clearly observe that the quasi-free K-binary absorption process, which is actually clear evidence of the existence of the intermediate K-bar during the reaction. So that the most natural interpretation is that this is a signal of the K-binary and going to lambda PDK. And by considering from the fit, we obtain the binding energy and width to the about 40 and 100 MBA respectively. But to compare these 2 values to the theoretical calculation, we should be pay attention because this is just a peak position of the simple Bragg-Wigner formula. On the other hand, in the theoretical calculation, they report the pole position, which is basically different from the observable peak position. But one theoretical calculation gives us the available as to the direct comparison between theoretical calculation and experimental result. This is done by the Sekihara, Osset, and Ramos. They provide the lambda p invariant spectrum like this. And black one is our data, and the red and blue dot dash line calculate spectrum. And as it is, calculated spectrum is very reproduced our results, so that theoretical calculation also supports that the observed structure is coming from the K-binary production. But of course, question always arises: is the observed resonance really what we expected, K-binary bound state? And is there any possibility to explain that without K-binary bound state, such as sigma psi bound state? Or if we can exclude such other possibilities, the question is that does K-bar really keep its particular identity in the bound state, in the resonance, in the observed state? Actually, it's difficult to exactly answer these questions at this moment. So to answer these questions, we need more evidence. So we would like to add more evidence by our new measurements. And we think there are 2 major directions. One is a systematic study for heavier chaotic nuclei, which has already done by Tadashi Hashimoto on Monday. And the other direction is more careful study for the K-binary state. And today I want to focus on this. And key issues for the K by N study is spin parity and a spin minus 1/2 state of the K by N. To do the new experiments, we have planned to construct a new cylindrical detector system, which is much larger than the current one. And by using this, we have planned to perform the systematic study for K9 nuclei. And this is a schematic picture of the new cylindrical detector system. An important feature of this is we can cover the more than 90% solid angle, and we will have a neutron detection capability and also sensitivity for proton polarization, which is very important to study more carefully for a K by N bound state. And we have got a large budget to construct the solenoid magnet and also a part of the detector system. So the construction has been already studied and completed in the 2025. And with this detector system, we can measure we can detect the neutrons so that we expect to observe distinct peak of the K by N with IZ for minus 1/2 state by not only the lambda and decay mode, but also sigma minus p decay mode as it is. And also the important thing is that the spin parity. And let's consider to determine the spin parity, let's consider the decay of the K by N going to lambda p. As I said, there are three different configurations for the K by N, but among these, the spin 3/2 state is already excluded because we measure the lambda. And so instead of this, let's consider the sigma n as spin 1/2 state, and which should be the spin parity of 2+ if it is an S-wave state. And to determine the spin parity, it is very important that spin and parity will be conserved in the decay because it is governed by the string interaction. So the most simple case is a spin parity of 0- case. In this case, orbital angular momentum of lambda p should be 1, and also the total spin of lambda p should be 1. And then consequently, the spin alignment of lambda p, denoted as alpha lambda p, will be +1. That means spin of the lambda and proton always parallel. Similarly, we can calculate the alpha lambda p for spin parity 1- and 2+ state as it is. And as you can see, we can separate these three different spin parity states by measuring alpha lambda p. And also, we can distinguish with these three different internal configurations from alpha lambda p measurement. So how to measure the alpha lambda p is rather difficult, but
3 minutes left.
Thank you. Thank you. We can measure, we can estimate lambda spin direction by its large decay asymmetry in the lambda going to p pi minus big decay. On the other hand, estimation of the proton spin is rather difficult, but we can do it by proton-carbon scattering asymmetry. By combining these two estimated spin direction, we will measure the azimuthal angle of these two estimated spins. And spin-spin correlation between lambda and proton will be observable as a phi asymmetry, azimuthal asymmetry of these two estimated spins. And we can deduce the alpha lambda p from the if we know the alpha asymmetric parameter or analyzing power of the proton-carbon scattering. And we have performed a feasibility study using the Giant-4-based simulation. And as it is shown, the left-hand side, this is a case of the spin parity of the - case. And on the other hand, if the spin parity of the K by N is 0-, we will measure we will observe the clear phi asymmetry like this. On the other hand, if the spin parity of the K bar and N is 1 minus state, 1 minus, observed asymmetry is very weak. So we can distinguish between 0 minus and 1 minus, as well as 2 plus state. So, and additionally, we can use the production cross-section ratio between Z7, the component to be plus minus one half. And combining these informations, we can determine the uniquely determine the spin parity of the K bar. Of course, we have planned the systematic measurement, not only for K bar and N, but also heavier system, as well as lighter system like this. So this is summary of my talk. First half of my talk, I summarized the result of this JPA-15 experiment, in which we observed the first clear signal of K bar and N. In the second part of my talk, I summarized the future plan of our experiment to robustly confirm the existence of K bar nuclei and clarify the internal structure. And we hopefully start this new experiment from 2026. So my important message is that if you are interested in our experiment, a kinetic nuclei experiment, or whatever using the large solenoid magnet with high intensity meson beam, let's do it together. Please join us. That's all. Thank you for your attention.
Thank you, Takumi, for this very interesting talk. We have several questions. Ozette, the first one.
Okay, you mentioned that this work of Sekihara and Ramos, which is very elaborate. You know, there is a dynamical calculation there, and one calculate the strength and everything. You know, it's not trivial. Now, for me, that was convincing that it was a real, that the K-bar and then bound state had been found. But the thing still remains, that Sekihara and us, we give, about 20, 25 MeV binding. And you claim you have 42 MeV binding. So I don't know, why that can be, because, we can live and we get the peak very well with 25 MeV. So, the 42 MeV probably is a little bit too large. And let me remind you, that this number has been going down with the time. At the beginning, some people claim 85 MeV because that makes Yamazaki happy. Then that went down, to 65. I have seen all these numbers in conferences. Then it went down to 55. Now it's 42. So, you just add there some systematic. You have just statistical errors. Add some systematic errors because, the reaction is very, very complicated, very level. So add, a little bit of systematic errors, and then you would make that compatible with this 20 MeV, which is not only, what we get, but what everyone that does chiral theory gets right now. All those you use chiral dynamics, they get about 20 MeV or so for the binding of that state. So you would make it compatible only adding a little bit of systematic errors.
Yeah. I believe that we should extract the pole position, exact pole position from the experiment to directly compare to the theoretical works.
To me, it's still a little bit of a puzzle why one calls this a K-bar NN signal if you don't see any trace of the K-bar in the system, apart from the initial state, of course. So again, isn't the really important primary question to understand how that 100 MeV width comes about? Because that implies whatever state it is, it lives for less than 10 to the minus 23 seconds. This is usually not called a bound state.
Yes, so to confirm that, we plan to perform this further experiments. But at least, including the width, our result is consistent with the theoretical calculation like this.
Microphone.
Well, the point is that one always underestimates in the discussion, I think, the role of K-bar NN absorption, right? Because this is, K-bar NN absorption requires kinematical conditions where the two nucleons sit close together, and the typical momentum transfer is of the order of a few hundred MeV. This is exactly the corner that you emphasize all the time.
No, stop. Elogio.
This is already taken into account in the calculation of Sekihara.
So,
In the calculation of Sekihara and Rambos, that is already taken into account, this K minus absorption. So that's no problem.
okay. I'm sorry, but we have to move on. Thank you again to the speaker. And now we have the last talk of the first series. Dr. Ramon Alea from the University of Brescia and and IFN Pavia. She will tell us how to constrain the K-bar and coupled channel dynamics using femtoscopic correlation with Alice and at the LSC. Please.
Okay, thank you for giving me the opportunity of presenting our work on this topic. So we can start briefly with an introduction. So we already see the introduction several times in these days. But okay, the main topic, let's say, is try to constrain the kaon-proton interaction. So you see here the results that have been collected so far at the scattering experiment. We can focus on positive kaon and negative kaon as approximation for kaon and k-bar, and focus on the data where there are more statistics. So we start with kaon over proton. So essentially we can see here the cross-section, and in the cross-section we can already see that for the K plus proton some interactions. So we have a repulsive attraction, not only related to Coulomb because of kaon and proton, but also related to some strong interaction which can be well described by the theory. Different is the situation for the K minus proton interaction, as you know. And this is the, let's say, the results of the scattering experiment. So we can see here that already from this data, the results are very different. And we can focus on the low part over here. So first of all, we see a very repulsive, attractive interaction. Again, not only because of Coulomb, but also because of some interaction which is strong. And we have the appearance of several resonances that decays in K minus and proton. And there is also another characteristic of this channel, as we have discussed several times, which is the presence of coupled channels. So coupled channels are states which have a mass which is similar to the K-bar N system, and that influence the interaction above threshold, but also below the threshold, and also the elastic part of the interaction. So we have seen several times from these coupled channels arise a special particle, which is the lambda 1405. And by studying, let's say, the dynamic of two coupled channels related to the K-bar N, so the K-bar N and sigma pi's, we have the formation of these resonances, which essentially, as we have seen several times, is a combination, is the dynamical formation, is composed by the dynamical interaction of two poles, essentially two coupled channels which are coupled to the sigma pi. So experimentally, this is below the K minus threshold, so it can be studied below threshold just by theory. And the different theories give different interpretation of this status, as we have seen several times. And above threshold, we have scattering experiment, as I showed you before. So more or less all the theories are able to describe all the data. And at threshold, the theories are all, let's say, constrained by the measurement of the Siddhartha experiment. So the question is it possible somehow to try and see if we can somehow help in understanding better the K minus proton interaction? And the answer is yes, and this is done with the two-particle momentum correlation. We have seen this technique already explained several times in this presentation, and here I have just reported all the paper that have been presented by, done by the Ellis collaboration on the topic of two-particle correlation, and among these 16 papers, 3 of them are related to the kaon-proton study interaction. So let's see briefly what is a two-particle momentum correlation and how we can use it to study the interaction. So essentially, what one can measure, it was already introduced, is this correlation function, which essentially is the ratio between the distribution of this variable, k star, where k star is essentially the momentum of the two particles that we want to study in their rest frame, divided by the same variable, k star, but taking the two particles from two different events, 2 or more different events. And these distributions are normalized such that for very large k star, the correlation function is 10⁻⁴, okay? Theoretically, this quantity, this correlation function, can be described by the so-called Konin-Pratt formula, and the ingredients are 2 essentially. The first one is the emission source, and I will show you how we focus, how we constrain the source for these channels. And the second part is related to the interaction. The interaction, which is essentially the is the wave function that can be somehow recovered by, described by the potential. So an attractive potential gives a correlation function below 1. A repulsive potential gives a correlation function which is larger than 1. So every time that we see a correlation function larger than 1, we have an attractive, something which is attractive. When it is smaller than 1, we have something which is repulsive. So the idea, is to measure the correlation function, fix the source, and then study the interaction. And this is what is usually done. What is new somehow here is that now we do not simply measure the correlation function in one colliding system, but we measure it in different colliding systems. Different colliding system means different source size. So proton-proton, more source size, lead-lead, large source size. So essentially what we can do is probe some different part of the interaction, okay? So this is what I will show you today. This is done with all the measurements are done with the Ellis detector, which essentially is one of the LHC experiments which is essentially suited for these studies. And essentially for the study that I will present you, we have used the whole statistics that was collected at the LHC in run 2. So proton-proton collision, proton-lead collision, and lead-lead collision, where in this case it means only that we have measured a lot of source size, from 1 Fermi up to 5-10 Fermi. Okay, so this is an example of the correlation function. So here we have a positive kaon and a proton. So the black points are the data. In the data, we see, first of all, that the correlation function is below 1. Below 1 means repulsive. More repulsive than a simple Coulomb interaction. So it means that there is also a strong repulsive attraction that can be somehow described by the models. Very nice. Now we can see what happened for the K- proton. For the K- proton, first of all, we see that the correlation function is above 1. Above 1 means repulsive. Repulsive more than a attractive, more than a simple Coulomb attraction between a positive and a negative particle. We can see also other different features in this correlation function. The first one is this bump over here. This bump over here is attributed to the lambda 1520 decay. So we have a lambda 1520 that decays in a kaon and a proton, and we see this resonance exactly where it should be, so 250 MeV, which is the momentum, the P0 of the decay of the lambda 1520. Then there is another feature, which is this bump. This bump that back in 2020 was not possible to describe by any model that we had, and this is attributed to the opening of the K-bar-N channels. So we see for the first time, these couple channels directly opening of this couple channel. And then we study larger systems. In larger systems, we see that the correlation function change dramatically with respect to what we have in proton lead. So essentially, all these structures somehow are washed out, and we have this correlation function. What is the difference between this case and this case? The difference is the source size. So we are probing different ranges of the correlation function. Let's see what the theory tell us about that. So essentially, in the presence of coupled channels, so we have K- and proton, and we know that we have coupled channels, the coupled channels that couples with the K-on-proton interaction. So essentially, the theory told us, well, without any coupled channel, the correlation function should be something like that, okay? Then we add the K bar n. K bar n is a channel which is above threshold, and whenever there is a channel above threshold, it appears as a cusp in the theory. A cusp in the theory, which essentially in experiment we see a broader, let's say, cusp because of the resolution of the experiment. And so this is what we see here. And then we add the other couple channel. The other couple channel are below the threshold of the K bar n. Below threshold means no cusp, but a modification of the correlation function. So you see here at low K star, so at low relative momentum, that the correlation function changes. And this is an example for a very small source size, so as for proton-proton. When we increase the source size, essentially the effect of the coupled channels is somehow washed up because, well, essentially because the source is so large that the interaction among the different particles is not visible anymore. So let's see how we can, let's say, probe if this interaction is correct. So essentially here what we have is this correlation function which has been modified using a modification of the Koenig-Pratt formula. So essentially the first part over here is exactly as we saw before, so, and it is related to the elastic part of the interaction, K minus proton that goes into K minus proton. And then we have this second part which is related to the different coupled channels. Different coupled channels which have their different weights and also a different source size that can be used to describe the fact that in one case we have K minus proton and in another case we can have, for example, lambda and pions. One of the ingredients that it is important to fix is this source size. So in order to fix the source size, we essentially did something very similar to what was done for proton chaos. So essentially the idea is that there is a common source size, a Gaussian distribution from which all the particles are emitted, and then there is a tail which essentially is populated with all the resonances that fits the different channels. So there are some resonances that decay in protons, and they add a tails to this Gaussian distribution. And of course, this tail is different if we consider proton, chaos, lambda, sigma, or whatever. So essentially what we do is something very similar, but instead of using proton-proton correlation, we can use K plus proton. K plus proton, we know the theory that is able to describe this interaction. So essentially what we do, we take the Koenig-Pratt formula that in this case do not have to be modified because we don't have coupled channel for the K plus proton. And essentially the potential which is able to describe this interaction, we know that. And then let's say the free part is related to the source size. So the source size, as I tell you, is a combination of a Gaussian core from which the R, the radius, is the quantity that we don't know, and the tail we populate by using some assumptions. So essentially by using how many particles, how many resonances are produced, and how many of these resonances decay in the channel that we are interested in. And essentially, this is what we get. So what we see here are three examples. So going from the right to the left, we have a result for lead-lead, so large size. And you can see that this large size is not that large because it's a peripheral collision, but in the end, we have a radius over the order of 2 Fermi. Then in the middle, we have an example from proton-lead collision, so small system, middle-small system on the order of 1.3 Fermi. And on the right, we have an example for the proton-proton collision. So proton-proton collision means around 1 Fermi of radius. Okay, so by this, we can fix this R core. The R core can be different if we considered kaon and proton or the coupled channels that couples with the different particles. At this point, we can fit our data with the decay minus proton data. So the source part here can be fixed how I have described you before. And this source can be different by considering different coupled channels. So each pairs, let's say, comes from a different source that we can evaluate. So it is fixed. What it is not fixed, I mean, the interactions are fixed. What it is not fixed, or we can try to fix, are these weights. These weights, which essentially takes into account how many particles we are considering. So in order to do that, what we do is make some assumption. The assumption that we make are essentially we evaluate by using the statistical hadronization model, the fraction of primary pairs. And then we distribute them in order to have a distribution in momenta. Because, of course, we need to consider how many of all the particles have a momentum which is close to the one that we are studying. And if we do that, then at this point we have some numbers. These numbers are normalized to the yield of K minus and proton. Okay? So these weights are all related to the channel that we are interested in, which is K minus and proton. If we do that, this is the results. So we can see here that for large system, using the theory that was described by Yodo before, we can describe rather well larger system, but then moving to smaller system, we cannot describe the data anymore. So it means that there is something which is missing in a model. In order to quantify, let's say, this discrepancy, what we do is say, okay, since we cannot modify the potential so easily, we add some new parameters. These alpha parameters, we call it alpha because in order to separate the weights. And these alpha parameters are one for each coupled channel, okay? And so we fit, and you say, okay, you add a few free parameters to the fit, and in the end, the fit is okay, fine, very, very good. You added a few free parameters, but at this point, we can see, okay, let's see how these parameters behave, because if they are random, it means that we simply add a systematic, let's say, 2 degrees of freedom, and everybody is good to do those fit. But what we can see here is that these are not randoms, okay? So we have here the weights related to the sigma pi in red and to the k bar n in black. And we can see that systematically essentially this k bar n deviates from 1, where 1 means that the theory is good, while different by 1 means that the different is not good. So essentially, we see that what it is implemented so far in the Kyoto model is not good to describe the data as a function of the correlation, or as a function of the source size. So this is the end. Since I already over my time, I let you with the conclusion.
Thank you, Ramona, for your nice talk. So we have time for one short question or comment. Angel Saramos.
Thank you very much for this nice talk. I wonder whether these weights, couldn't you get them already experimentally? Because you are counting number of pairs. So could you just count number of, maybe it's very difficult, I'm a theorist,
No,
so I don't know how.
Some of these particles we cannot measure directly.
Okay.
So what we do is we take the particle that we can measure, then we fit them with a version of the statistical hadronization model, and then we assume that this is the same also for the particle that we cannot measure, because, for example, the sigma 0, we cannot measure it. I mean, we can measure it, but not so precisely. The sigma plus and sigma minus, we didn't measure them yet. The neutron we cannot measure it with
Okay,
Alice.
thank you.
Onishi-san?
Thank you very much for your nice talk.
Question, not speech.
Not speech. Question, okay. Okay. I think that the I equal 1 K by N interaction is information, experimental information is very scarce for I equal 1 K by N interaction. Is there any way to extract I equal 1 K by N interaction using femtoscopy or other method?
I couldn't hear what particle you want us to measure, sorry.
I spin 1. K minus neutron
No, we
or
cannot
K0 bar proton?
K0 bar proton? Well, for the K0 bar proton, we have measured K0 short proton, but still in this case, we have the combination of K and K bar. And this we have
Maybe
measured.
K minus deuteron.
K minus deuteron,
Help.
yes, it's ongoing,
Thank you.
somehow.
So thank you. Let's thank again Ramona. And now we move to have a look to the future. So I would like to invite Professor Satoshi Nakamura from the University of Tokyo. He will talk about the future prospects of spectroscopy of lambda hypernuclei at JLab and JPark.
Okay. Let me start the future prospect. Actually, I put some, this is the wrong title. Maybe I updated it, but the spectroscopy of the lambda hypernuclei at JLab and JPark, which I saw. And I'm now coming from the University of Tokyo. And so already we already listened to many speakers discuss about the Hyperon puzzle. Hyperon puzzle is one of the important questions for the Nuclear Physics Society, and we should answer. And you already know, so I'm not repeat much, but this is the famous the radius and mass of the neutron stars. And if you give some of the equation of state of the potential model, then you can have the one line. And if inclusion of the hyperon, that makes the equation of state soft, and it cannot support a very heavy neutron star, and it will collapse to be a black hole. And it is obvious that we need to have some additional repulsive force to make the equation of states differ. And one candidate is the inclusion of the three-body repulsive force. And so in order to, this one is one example, the calculation by the quantum Monte Carlo, and the Abraham already pointed out this one is too naive. But anyway, other calculations also give the similar tendency, so we need some additional repulsive force to make the equation of state stiffer to support the two solar mass, the neutron stars. That one is, we know that exists in our universe. And the recent astrophysical observation of the neutron star, that one is quite a nice result. Now we have from the gravitational wave of the neutron merger, and nice neutron star X-ray hotspot measurement gives a very recent interesting result about the size and mass of the neutron star. And I would like to emphasize now the CRISM, the X-ray imaging and spectroscopy mission, the new satellite will be launched in this Japanese fiscal year. So we will have the more new astronomical observation data. And so now we will have some macroscopic understanding of the neutron star. That one we will have the written of the data in near future. But we need to understand why the neutron star is so large and so heavy. So from this kind of the macroscopic data to extract the equation of state or some hyperons, the nuclear interaction, that is the inverse problem. So we would like to have the microscopic understanding from the terrestrial experiment, and both of them, that's quite important to have the complementary approach. And this is the strategy they have to attack this problem. And as already Miwa-san mentioned, we will have the good data for the hypernuclear scattering experiment. And the femtoscopy gave lots of the new information. So we will have the realistic two-body baryonic interaction. And but when we would like to calculate the neutron star property or the hypernuclear property, we need to convert this information to the immediate baryonic interaction. So the density dependence or the three-body force, that information, that one is we need to extract or extend using the well-established technique to convert this two-body baryonic interaction to this information effectively the potentials. And then we can compare the result of the high-precision data from the hypernuclear spectroscopy. So the right hypernuclear system, that one is important to give some low energy constant for the chiral effect field theory, or we can test the realistic two-body baryonic interaction. And then this immediate baryonic interaction that can be tested with the medium to heavy hypernuclear. So we need to perform the experimental study for from light to the medium and heavy. So very wide range of the spectroscopic study. That one is quite important. Then we will have the equation of the neutron star, and we can use such kind of information as a touchstone comparing to the macroscopic astronomical observation from the gravitational wave, the X-ray telescope, and so on. Okay, so so far we have several ways to produce the lambda hypernuclei, and one method is E-chemical reaction spectroscopy established at the Jefferson Lab, and it features excellent mass resolution, the some MeV, and we can calibrate the energy scale using the proton target and lambda or the sigma zero, the known mass to hyperon production. We will calibrate the energy scale. And we will have the very high intensity beam, the 100 microampere of the electron beam that corresponds to the 6 times the 10 to 14th per second beam. So it is important. We cannot measure the energy of the electron one by one. It is impossible. So we should rely on the accelerators, the information about energy and position of the beam. And thanks to this strong beam, that we can use the thin target. So the luminosity that we can gain from the intensity of the beam. So the isotopically enriched the precious target, for example, the calcium-40 or calcium-48, or even the tritium target we can use. And for the conventional, the meson beam reactions, so K minus pi minus or the pi plus K plus reaction, that one has the intensity limitation because they cannot, the meson beam cannot directly accelerate it by the accelerator. So we need to accelerate the proton and produce the meson beams. So the intensity of these beams a few times 10 to 6 per second. That one is the conventional limitation. And the resolution of these spectroscopic, that one is again due to the quality of the beam, the 1 to a few MeV resolution. That one is the best achieved performance. And we need to normalize the result to the carbon-12 lambda, the known hypernuclear mass. But the situation will be changed when we realize the high intensity, high-resolution beamline and the Hadong extension hole. We can enjoy the excellent mass resolution. That one is even better than the E-chemical reaction spectroscopy. And we can use the thin target isotopically enriched. That is the same feature for the JLab experiment. And we can remove the limitation for the beam intensity. So actually the JPEG's the meson beams intensity, especially for the pion, we can have more. But the event by event measurements of the beam, the energy, that one prevent us to use the very strong the meson beams. Okay, so this is the picture of the previous Jefferson Lab's experiments. So E-chemical reaction spectroscopy using the Kaon spectrometer and the electron spectrometer, and we have the charge separation magnet here. And you can measure the Kaon and the scattered electron in coincidence. But for the electron beam, we know the energy and position on the target, so we need not to measure the electron beam's property. And So we already have the 3 experiments approved. And one is a calcium-40 and the calcium-48 target, and the E'K reaction will convert the proton to the lambda. So that we will have the potassium-40 and potassium-48 lambda. And the Akiyama already presented about this experiment on yesterday, the day before yesterday, the pasta session. And cryogenic gas targets for the helium-3 and the helium-4 targets, then we will have the hydrogen, so hypertriton and the hydrogen for lambda. So the hypertriton, we have some discrepancy between the lifetime and binding the energy. So that one is important, and that one is one of the quite important for the measuring the binding energy. And we will measure that one at mines, but at the same time, we can perform the spectroscopic measurements using the E'K at Jefferson Lab. And hydrogen for lambda, the Gogami already mentioned, presented at the poster session. This one we can measure the excited state of the hydrogen for lambda, so that one is quite important and interesting. And the red target, we will produce the thorium-208 lambda, and after this session, Franco Garibaldi will discuss about it. So from the picture shows the mass dependence and the asymmetric parameters, the isospin unbalancedness, and the neutron star is the neutron very rich material and very large the mass number. And we have, so far that we used only the solid target and stable one. So once we determine the one target species, then converts the proton to the lambda, in that case, automatically, what kind of the hypernuclei can be studied, that one is determined. And the 3 experiment approved ones, that one will targeting the right, and we will have the potassium-40 and 48 to study the isospin dependence, and the heaviest hypernuclear program for the red target experiment. Okay, then again, this one is already Abraham pointed out the Rodolphi's calculation. That one, the 2 naive the potential, that one used, but we need some of the guideline to design the experiment. And actually, in his calculation, he changed the strength of the lambda and the contribution to the isospin triplet part by hand, introducing the CT parameter. And then changing the CT parameter by hand, and that will change the relative ratio between the isospin, the singlet, triplet. So the behavior for the isospin balance or the isospin unbalanced hypernuclear, the binding energy will be changed depending on the CT. So when we compare the spectroscopy of the potassium-40 lambda and the potassium-48 lambda, then we have this information. Of course, with this, Abraham gave yesterday, we heard another type of the calculation that it looks quite interesting. So we encourage the scientists to calculate and provide us more information about the theoretical study. So this is just one example, and we would like to have the other type of the calculation. Okay, then we already designed the new experimental setup for the design for the whole A at the Jefferson Lab, including the new the charge separation, the period of the charge separation magnet, the PCS, and we increased the beam energy from the whole C option to the 4.5 GeV from the 2.5 GeV to make the backgrounds more forward, and the background for the electron arm that will be reduced much. And we will have the pair of the charge separation magnet instead of the one big splitter magnet. Then we can separate the optics system for the electron arm and the kaon arm. And we have the HRS instead of the HES for the whole A option. So we will have the vertical bending spectrometer, and that one gives the vertex information along the beam line. So even though we use some gaseous target, we know where the reaction point is. And the construction of the pair of charge separation magnet we already did in Japan. And actually, just the beginning of the COVID-19 pandemic, we already finish the construction of this magnet. And finally, beginning of this year, our magnet arrived to Jefferson Lab. So we spent 2 years for the transportation of this magnet from Japan to the United States. But anyway, now these magnets are ready at the Jefferson Lab. And another constraint for us is the whole A. We have the too many experiments in Q. So we need to move to the whole C rather than performing the experiment in the whole A, because the whole A, scheduling that one is too tight, and no one tells when we will have the realistic beam time assignment. So in that case, the whole C, there are the standing to the spectrometers and quite tight, but it is possible. And we have no HRS in the whole C, the Jefferson Lab, so we need to use the HES as a electron spectrometer. So in that case, we should reduce the electron energy again to the 2.5 dB. And if we want to use the gaseous target, in that case, we should have the vertical bending type the spectrometer. So that we are now considering to design the convert or the modify the HES or the HKS, at least one of them, to be a vertical bending type spectrometer. So we plan to ready for the beam in the year 2024 to 2025, but we need some re-optimization of the experiment. And for the JPOC, already Tamara-san explained about we have the future plan for the extension of the Hadong hole. And Sakuma-san will give the detailed discussion about this project. And we will, yes? Okay, we will have this extension hole, so the Hadong hole will be doubled. And we will have the HIHO, the high intensity, high resolution beamline. That one is one of the flagship the beamline in the Hadong hole extension project. And I would like to concentrate on the beamline and the hypernuclear program there. And the high intensity, high resolution beamline, we will introduce the momentum dispersion matching technique. So actually the K-on spectrometer and the pion beamline, that one will be operated simultaneously, or the design, that one is to fit each other. And I will explain later about the concept of the dispersion matching technique. But we can have the over the 200 million pion per pulse. So conventional the beamline, that one a few times 10 to 6 pions per pulse, and the beamline resolution is 1,000. But for using the HIHO, the resolution for the beamline, that one is 10 times better, and the beam will be stronger than 200 times. And this is the concept of the momentum dispersion matching. So we will have the beam position, angle, and momentum. And then beamline, the transfer matrix, this is the lowest order, the beam transfer matrix. And we have the target and the reaction to produce the hypernuclei. And the K-on spectrometer. And then at the focal plane, we have the position, angle, and momentum vector there. And this position information can be written in this way. And you can see this the first the term that can be cancelled when we try to minimize these terms. So total cancel is difficult, but we can minimize. And the point-to-point focus on the momentum matching and so on, these parameters can be adjusted to be 0. So it is possible using some degree of freedom of the beamline and the spectrometers. Then we can cancel these 3 terms. Then the final, the position at the focal plane can be directly translated to the excitation energy of the reaction. So we need not to measure the pion energy event by event. Actually, that will be canceled automatically. So just measuring the focal plane position, then we can have the excitation energy. That is the concept of the momentum dispersion match technique. So using these techniques, we can improve the pi k spectroscopy resolution from these this is the old red 208 lambda the hypernuclear spectroscopy performed at KKPS, and we can have this kind of the spectroscopy. So the resolution will be outstanding. And we can see previously the background, we can separate these sub-peak component. So we can convert the background to the new signal information. And that one is the comparison between the E prime K is the carbon 12 lambda, and this is the expectation, the carbon 12 lambda is the HRHR. So if we have the HRHR, then these resolution can be matched for the first time, so that we can have the real, isospin independent study with the similar resolution for the pi K and the E prime K. Okay, so the time is gone. So we will perform, we already submit the proposal for the wide variety of the target, but this is the first campaign. This is not the end of the project. So we propose these targets, and in total, it's the 100 days for the beam time. And our goal is the peak determination precision for 40 kb FWHM. That corresponds to the sigma of 17, so better than 20 kb. So let me summarize my talk. So the recent progress of the astronomical observation of the neutron star, that one urged us to the microscopic understanding become more important. So the high precision spectroscopy of the hypernuclear, that one is quite important. So we would like to, so we already have the 3 programs at the Jefferson Lab, and HRHR, that one is really, with your support, that one, we hope that we will realize soon. Then we can perform the new pi-K spectroscopy using the dispersion match technique. And we would like to realize hypernuclear factory in Japan. Thank you very much.
Thank you, Nue-san, for your exciting review. I wish you all the success. So, questions, comments? Horst.
A very interesting project indeed, and I think a very important project as well, because also, since you have a whole list of medium and heavy nuclei included, I think that is quite important to have progress also in the understanding of the real saturated nuclear matter, so to say. The light systems are very interesting to understand the individual effects like the 3-body problem, but these heavy systems, they are so important to understand really how hyperons behave in a saturated nuclear matter environment. So I think that is a good perspective.
Yeah, thank you very much. So this is just the first campaign. So after this campaign, we can have the more target. So the second, third campaign we are expecting.
Any other question, comment? If not, let's thank again Satoshi Nakamura. And now I would like to invite Mifuyo Ukai from KK. She will give us a summary and the future prospect about the hypernuclear gamma ray spectroscopy.
Hi, I am Mifuyu Ukai from KK and Tohoku University. Title of my talk is Hypernuclear Gamma Ray Spectroscopy, Summary and Future Prospect. This is my contents. Today, I will talk about 2 topics, lambda N interaction study from light hypernuclear gamma ray spectroscopy, and another is the E-medium lambda G factor, which can be measured by BM1 of the spin flip M1 transition. This is a level hypernuclear gamma ray data of at present. S shell to SD shell hypernuclear level structures were precisely measured by a germanium detector, and some are measured by sodium iodide. Today, I will introduce the result of helium-4 lambda hypernuclei. It was performed at JPAC. And gamma ray spectroscopy, or topic of gamma ray spectroscopy is very variety, but today I will show the charge symmetry breaking. And I will introduce future plans. One is light hypernuclei. One is helium-4 lambda to search charge symmetry breaking. And another is gamma ray search of hypertriton. This experiment will be approved at JPAC E63 at K1.1. And another topic is spin flip BM1 and in medium G factor. One is lithium-7 lambda ground state spin flip, and it is also approved as JPAC E63. And I will show another new experiment as carbon 12 lambda ground state spin flip BM1. And we have another topic, but today we skip it. So let's start gamma ray spectroscopy of 3 and 4 body hypernuclei. This is E13 experiment. JPAC E13 experiment performed in 2015 at K1.8 beamline. The reaction is the target of this experiment is helium-4 and using the K-pi reaction. And helium-4 lambda excited state was produced directly by K-pi reaction. This is a missing mass and we can observe the ground state peak and gating here, and we see the gamma ray spectrum. Then we can clearly observe the helium-4 lambda gamma rays, the energy of 1.4 MeV. The gamma ray energy was measured by germanium detector array hyperbole. So from this 1.4 MeV spacing, the 4-body hypernuclear level scheme is reconstructed. The ground state of hydrogen 4 lambda and helium 4 lambda was precisely measured by immersion using the same technique. In all the data, the ground state of these values suggests charge symmetry breaking. And all the sodium iodide data show this spacing is 1 MeV. And our data show this spacing is 1.4. Then the charge symmetry breaking between lambda p and lambda in interaction and its isospin determinant is confirmed because 0 plus have a large difference, but the excited 1 plus is almost the same mass. However, the measured energy of hydrogen 4 lambda is not precise because this is old data from sodium iodide. The hydrogen 4 lambda was performed measured 3 independent experiments, but these experiments report the different center values. So we propose the E7 63 experiments to measure the hydrogen for lambda. So I will introduce how to produce the hydrogen for lambda excited state. The hydrogen for lambda excited state cannot produce the conventional K-pi or pi-K reaction, non-charge exchange reaction. So we choose the target to be lithium-7. The lithium-7 is alpha plus triton cluster. Then lithium-7 lambda can decay to helium-3 and hydrogen for lambda. The lithium-7 lambda of the highly excited state, such as S substitutional state, can decay to hydrogen for lambda. The expected yield ratio of 1 plus and 0 plus is 3:1. And this is a byproduct of E63. So as I said, lithium-7 is alpha plus triton cluster. So the hypertriton can be produced as substitutional state on this triton. So the production of hypertriton is expected to be a large cross-section. So this is an expected level scheme of NM lambda system if NM lambda is bound. So if NM lambda is under this particle threshold, this isospin 1 state is probably under this threshold. If so, the gamma ray transition to ground state doublet is expected. But recent JLOB data report negative for existence of bound state. But even if this isospin 1 state is slightly higher than the threshold, but there is a chance to have a finite branching ratio of gamma decays. So the hypertriton is the lightest hypernuclei, but the situation of recent experimental data is becoming chaotic. So germanium detector is a well-calibrated detector. Systematic error is less than 1 keV, and the resolution is a few keV at 2 MeV region. So if we can observe hypertriton gamma ray, the problems of different experiment values of hypertriton binding energy and the existence of NN lambda would be solved. So to identify the hypernuclear species, we will use a triple coincidence method. This is reported by Oura-san yesterday. We use a missing mass technique. We select the missing mass region here, and we will measure the weak pi minus energy. The kinetic energy of two-body decay of pi minus is 53 MeV and about 40 MeV. So we developed a range counter. This is a photo of a prototype, and we already tested by using a beam. Okay, I will show another topic: spin flip BM1 and in medium G factor of lambda. This schematic view shows the G factor of lambda is different. In nuclear medium, the G factor of lambda is different from free lambda. And this picture shows the low-lying level scheme of a hypernuclei. If the core nuclei has spin J, the hypernuclear level split into two spin doublet. This is a lambda spin flip M1 transition. This M1 transition widths have information of G factor of lambda and the core, like this. So if we can measure this BM1, we can get the G factor of lambda in nuclei. And this BM1 can measured by the lifetime of upper level. So expected M1 width value of right hypernuclei is shown here as lifetime picosec. And this is all measured value. And so lifetime measurement method is one is a Doppler shift attenuation method. This is a gamma ray peak shape analysis. If the lifetime is the same order as the stopping time, we can get the lifetime of this state by the peak shape analysis. So if the lifetime is much larger than stopping time, the response function of the gamma ray peak shape is the same as response function of germanium detector. But if the stopping time is almost the same order, the peak shape is widened, partly widened. So we select this candidate as lithium-7 lambda. To match the stopping probability, we developed a lithium oxide single crystal. This is a simulation. This experiment is accepted as E63, and this is a result of simulation. We can get 3% accuracy. And I will introduce another method, the direct measurement of our lifetime here. So if the BM1 is compete with weak decay, the part of hypernuclei decay to M1 and part is weak decay. The carbon-12 lambda ground state is energy splitting is very small. Then the BM1 is expected the same order as weak decay. So we can measure this lifetime to one is lifetime by weak decay particle detector, detecting the weak decay pi or proton, and one is lifetime by gamma ray detector with good resolution gamma ray detector. So this is a candidate of gamma ray detector. This scintillator has a very fast decay constant. And this picture shows the conceptual design around the target with existing HyperTPC and Helmholtz magnet. This is already used in E42. And the realistic yield estimation is now undergoing. Okay, this is a summary of my talk. S-shell and SE-shell hypernuclear gamma ray spectroscopy were carried at KK, BNL, and JPAC. The observation of 1.4 helium-4 lambda gamma ray confirms the large transit symmetry breaking in the lambda-N interaction. And further study of charge symmetry breaking, precise measurement of hydrogen 4 lambda gamma ray is planned at E63, and E63 byproduct, we will perform the hypertriton gamma ray search. And the BM1 of the lambda spin flip M1 transition has information of G factor, G lambda in nuclei. And we now, today I propose the two type of BMR measurement. One is lithium-7 lambda ground state spin doublet with Doppler shift attenuation method, and a new BMR measurement of carbon-12 lambda is using the fast scintillation counter. This is not using hyperbole J, and as gamma ray detector for gamma weak competing state. That's all.
Thank you, Mifuyo-san, for your interesting talk. So we have time for questions, comments. Take Saito. Over there.
Thank you very much for a very nice talk. Could you go back to the slide showing the hypertriton and then lambda level scheme, talking about the gamma ray stuff? Yeah, this one. So are you saying that the 3/2 state is bound or exists for the t equal to 0?
If this state is bound, this state is also bound.
This is observed already for the hypertriton? No. Not yet observed, right?
Not, or only this state, because nuclear emulsion can't detect excited state.
Yes. So now I think if this 3/2 state with delta t equal to 0, exists, I think this is also have some implication for the lifetime of the hypertriton, because so I suppose that this transition from the 3/2 state to the ground state has lower gamma ray energy. This means that if I just remember the Weisskopf unit for this, the M1 transition, and then the probability may be small, so this means that the 3/2 state has some certain lifetime, and then when I remember, for example, for the few hundred kV gamma ray or something, then I think the lifetime by the Weisskopf estimation could be something like few hundred picosecond.
This state?
Yeah, if it exists. So in the heavy ion experiment, including our experiment, so we can also produce this 3/2 state.
But
in the heavy
this
ion,
3/2 state can decay to D plus lambda.
Only to the D plus lambda? Why not having the M1 transition of the spin flip?
Because the M1 is much slower than this transition.
But you are here assuming that the binding energy is only 130 kV, right?
I think this spacing is about 1 MeV or so. I expect it because
yes, then it is above the particle threshold. So therefore, so you are thinking that the D plus lambda going there, right?
If you say
But
that
here you
this
assume the 130 keV binding energy, right?
binding, your expectation of binding energy is larger than 1 MeV?
Well, this we don't know. Of course, I'm not expecting that larger binding energy, but we have no conclusion for the binding energy right now.
If
Okay,
this,
sorry to interrupt
Okay,
you.
so maybe we can discuss in the
We can
coffee break.
continue
Yeah.
the discussion over the coffee break. Here in the front line.
Yeah, I would like to also comment to this slide. I mean, first of all, it is, let's say, kind of, let's say, very dangerous, let's say, to claim that if you have, let's say, some excited state, it is immediately, let's say, a resonance and it can decay through a gamma decay.
yeah,
In case of, let's say, S waves, let's say S-wave state, which is here, this is, let's say, dominantly, let's say, governed by, let's say, this is basically L equals 0, total orbital moment to 0. So it is likely that it is a virtual state, and then you would not see any gamma decay, even if there would be an excited state. Second of all, let's say recently in one of our publications, we actually determined this M1 transition from 3.5 plus to 1.5 plus. This, of course, let's say, depends on, let's say, how far this excited state is from the bound state, but it is not correct and it is not true that actually, let's say, this M1 transition does not dominate.
right.
Yeah. So this is my comment, which I would like to say.
The last question.
Thank you. So it's very important that you are planning to remeasure the gamma ray in hydrogen for lambda. And can you say when you expect the first results of that, and whether you can reach the good resolution as the one for the helium-4 lambda?
So sorry.
So, so the quick question: when you expect the first result of the such measurement? Because yesterday the STAR collaboration reported much different results as we've seen so far.
You said when this E63 experiment will be performed, it is.
I mean, when you expect the result?
We want to perform this experiment at K1.1 at JPark, but the K1.1 is a conflict with another beam line. So, we can run anytime, but sorry, this is very difficult, and it depends on the Hadron Hall extension program. So sorry.
So the time schedule is still not defined.
Yeah, not defined.
Okay. So let's thank again Kai-san.
Before you leave, I have a small announcement. First of all, we ordered sun for this afternoon, so
it's time to start our next morning session. We will continue with a talk by Professor Umeya from Osaka on hypernuclei production spectroscopy with an extended shell model. So, please.
Thank you, Chair. Can you hear me?
Yes, yes.
Okay. Oh, okay. Okay, thank you, Chair. I'm Atsushi Umeya from Nippon Institute of Technology. Today, I'd like to talk about hypernuclear production spectroscopy with an extended shell model. My collaborators are Motoba-san and Itonaga-san. In production of hypernuclei, E'-K+ reaction experiment with high resolution have been performed at the Jefferson Laboratory. Furthermore, new projects of K-, pi- and pi plus K+ reaction experiments with high intensity and high resolution are being at JPAC. Detailed look in JLabo E'-K+ spectroscopic data requires an extended description with multi-configuration parity mixing mediated by Hyperon. We have extended the model space by introducing the new configuration, which includes non-normal parity nuclear core excited states. We will show the DWIA cross-sections of K-, pi plus K+, and gamma K+ reactions. We focus on the p-state lambda hyperon in the p-shell lambda hypernuclei. The recent E'-K+ reaction experiment for boron-10 target has been done at the Jefferson Laboratory. The upper figure shows the experimental cross-sections, and the lower figure shows the theoretical cross-sections by using the conventional shell model. This experiment has confirmed the measure peaks number 1 to number 4 predicted in the DWA calculation by employing the lambda particle in S orbit coupled with the nuclear core states confined within the p-shell configurations. However, it is interesting to observe extra strengths at the MEB excitation like this. This result suggests that the extension of the model space is necessary, and it is an interesting challenge in view of the present hypernuclear spectroscopy. I'd like to explain the extended shell model. In the conventional shell model, only natural parity nuclear core states are taken into account. A lambda particle is in the 0s orbit, like this. In extended model, we take into account one particle, one hole, one h bar omega configurations for core nuclear state and the p single particle state for the lambda hyperon. In the positive parity state of barium-10 lambda, the energy difference between the 0s lambda and 0p lambda is 1 h bar omega, like this. And the energy difference between the barium-9 natural parity core and barium-9 unnatural parity core is 1 h bar omega, like this. By lambda n interaction, natural parity nuclear core configurations and unnatural parity nuclear core configurations can be mixed. In the conventional shell model, only the 0 h bar omega nuclear core is considered, like this. In this work, we consider the 1 h bar omega nuclear core for hypernuclei, like this. In order to allow the barium-10 lambda production through various configurations, we extend the model space for target nucleus boron-10 up to 2 particle 2-fold configuration, 2 h bar omega configurations. Okay, this figure shows the energy levels of barium-10 lambda together with those of the barium-9 core nucleus. We obtain various states of barium-10 lambda hypernucleus with positive and negative parity by using the extended shell model. We obtain the states which correspond to the new bump observed in the JLab experiment. We can extract typical states through the differences in the characteristics of K-, pi plus K+, and gamma K+ reactions. We have calculated the production cross-sections for PCR hypernuclei by using the extended shell model. This figure shows the numerical results of cross-sections of the gamma K plus reaction for boron-10 target, which correspond to the E prime K plus reaction experiment at J level. The DWI cross-sections are based on the elementary amplitude circulated ion model A. Our new calculation reproduces the 4 major peaks, number 1 to number 4, which have already been predicted in the DWIA calculation by Motoba-san. We emphasize that the present calculation by using the extended shell model configurations can provide us with new positive parity state at the right position. That corresponds to the new bump of the J-level experiment, like this. These non-normal parity states have not been obtained in the conventional shell model calculations exploited so far. This table shows the theoretical and experimental values of the cross-sections, theoretical calculations, and experimental value. Our new calculation results are in good agreement with the experimental data. The major peaks are explained as the doublet state, like this. The new boron bump is successfully explained with the peak broadness being attributed to a group of several positive parity states newly obtained in the present extended shell model. In more details, one sees that the new bump A should be explained as the sum of cross-sections of several positive parity states. We investigated configuration mixing between the natural and unnatural nuclear core in the positive parity states, which correspond to the new bump. This table shows the large mixing in 4 positive parity states, like this. The bump in the cross-sections of barium-10 lambda will be explained by the splitting of P lambda state in the deformed core nucleus. In barium-9 lambda, it is well known that the P lambda state splits into 2 orbital states expressed by P perpendicular and P parallel, like this, which is due to the strong coupling with nuclear core deformation having the alpha-alpha structure. We calculate the cross-sections of the K minus pi minus reaction for the barium-9 target in the extended shell model. Our new result is in good agreement with the cluster model calculation, like this. This small peak denotes the P parallel state, and this large peak denotes the P perpendicular state. In these figures, we compare the DWI cross-sections with the experimental data for the K minus pi minus and pi plus K plus productions for barium-9 lambda. In the pi plus K plus production, the peak number 3 in experiment is explained by the P parallel state in the present extended shell model. Okay. In order to understand the structure of the new bump in the barium-10 lambda production, we calculate the cross-sections of the K minus pi minus reaction for the boron-10 target. In the K minus pi minus reaction, the large peak at 4.4 MeV is a P substitutional state from nucleon P3 halves to lambda P3 halves, which is strongly excited by recoilless reaction, like this. The small peak about 0 MeV corresponds to the new bump, and it is explained as a mixture of S lambda and P lambda states. The large peak at 4.4 MeV in barium-10 lambda corresponds to the P lambda perpendicular state in barium-9 lambda, which is barium-9 analog state. The small peak about the MEB in barium-10 lambda corresponds to the p lambda parallel state in barium-9 lambda. The alpha-alpha-like core deformation causes splitting of p lambda states. Then low energy p parallel state can mix with s lambda state. These parity mixed wave functions at the MEB can explain extra peak A. Okay, now I'm going to show the result of boron 11 lambda. We calculate the cross sections of the K minus pi minus and pi plus K plus reactions for the boron 11 target in the extended shell model. The upper panel shows the cross sections of K minus pi minus reaction with the 1.1 dB over C incident momentum. The lower panel shows the cross sections of pi plus K plus reaction. For two peaks, we investigated probabilities of the main configurations. The large peak A corresponds to the substitutional state, which mainly consists of 3 configurations, and this state can be considered as P perpendicular state. In the peak B, the eigenstate mainly consists of 2 configurations, and this state can be considered as P parallel state. Here, I show the energy of P parallel state for A equal 9, 10, and 11 hypernuclei. The P lambda state split into P perpendicular and P parallel states due to the strong coupling with nuclear core deformation. In barium-9 lambda, the energy of P parallel state comes down to EX equals 7 MeV from the lambda single particle energy differences of 11 MeV. In the cross sections of barium-10 lambda, the bump at EX equals 8 MeV correspond to the P parallel states. In the cross sections of boron 11 lambda, the small 5 halves peak at EX equals 9 MeV correspond to the P parallel state. The energy splitting between P perpendicular and P parallel states in boron 11 lambda is smaller than that in barium-9 lambda, which is due to the small deformation of the nuclear core in boron 11 lambda. In the spherical nuclear core, P lambda state does not split into P parallel and P perpendicular states. The new type wave function should appear in barium-9, 10 lambda and boron 10, 11 lambda due to the core deformation, but not in spherical systems without enough deformation. Okay, let me summarize this talk. We have calculated the DWIA production cross-sections for P-shell hypernuclei by using the extended shell model. Strong coupling between P lambda state and core deformation is realized in barium-9, 10 lambda and boron 10, 11 lambda. In these nuclei, P lambda states split into P parallel and P perpendicular states. In barium-10 lambda, the lower P parallel state comes down in energy and couples easily with S lambda state. Such new type wave functions should appear in barium-9, 10 lambda and boron 10, 11 lambda due to the core deformation. The finding of peak A in boron 10 E prime K plus barium-10 lambda production is a novel evidence for Gini hypernuclear wave function with parity mixing realized in deformed hypernuclei. Thank you for your attention.
Thank you very much for your very interesting talk. Now, questions, please. Oh. No.
Ume-san, thank you very much. Could you extend this kind of calculation to the heavier systems? For example, we are planning to land at the Jefferson Labs the aluminum target to the magnesium 27 lambda, and Isaka-san calculates the triaxial deformed one. Could you apply your calculation technique to the similar way to the magnesium 27 core plus lambda? So
yes. Yes, I can. I will calculate the aluminum 28 lambda.
27, yeah.
In the extended shell model.
Yeah, yeah. Mm-hmm. Yeah.
Yes, I can.
Okay, yeah, that sounds good because that one I have the hopefully that is triaxial, so maybe a little bit complicated, but yeah, but the similar structure should appear.
Yes.
Yeah. Thank you very much. It may be difficult, but yeah, it is a challenging theme. Yeah, thank you.
Okay, next question.
Thank you very much.
You had? Or if there are no other questions, thank you once again.
Thank you very much.
And now we will continue with next online lecture by Dr. Fujioka on production of light chi-square hypernuclei, particularly 7 chi-square hydrogen. Please.
Hi. Yes. Hi. Can you hear me? Excuse me. Can you hear me?
Yes, yes.
Okay. Let me start my talk. Today I'll talk about production of light cascade hypernuclei, hydrogen 7 cascade. My name is Hiro Fujioka from Tokyo Institute of Technology. So I talk about hypernuclei with strength -2. So maybe, as you know, so we have two kinds of double stranded hypernuclei. The first one is double lambda hypernuclei, in which 2 lambda hyperons are bound. And the second one is cascade hypernuclei, in which a single cascade hyperon is bound. And so these two objects are related with each other due to the small mass difference between the cascade nucleon system and 2 lambda systems. The mass difference is as small as 28 MeV. So it can be compared with the mass splitting between lambda and sigma or nucleon and delta in strength -1 or strength 0 sector. So these two objects are coupled with each other due to cascade nucleon lambda coupling. And today, maybe I focus on this cascade hypernuclei, but I show some status of this double lambda hypernuclei study in JPAC. So in previous HYPE conference in 2018, I talked with this slide. So in this slide, I focused on this hydrogen 5 double lambda production. So, and it is related to this hydrogen 7 cascade. And the content is almost the same as the previous presentation in HYPE 2018. But today I focus on this hydrogen 7 cascade. And after the HYPE conference in 2018, we submitted a proposal to JPAC regarding the decay pion spectroscopy of hydrogen 5 double lambda. So this is the E75 experiment at JPAC. 1 year later, we again submitted another proposal to JPAC about hydrogen 7 cascade production. So this is the E75 phase 1 experiment. So this will be done in near future, actually probably in 2023, next year. And today I focus on this hydrogen 7 cascade. So historically, these two kinds of double stranded hypernuclei, namely cascade hypernuclei and double lambda hypernuclei, have been studied by using nuclei mergons, namely cascade hyperons captured by light nucleus such as carbon, nitrogen, or oxygen in nuclei mergon, and these two objects are studied. For example, Nagara event for this double lambda hypernuclei or Kiso events, and so on. But in near future, we are about to take data with K-K plus reaction to populate this beryllium-12 cascade by using carbon-12 target. So this is the E70 experiment. to be carried out in next year. And with the same technique, I mean the same reaction, we can produce hydrogen-7 cascade from lithium-7 target. So this is the E75 phase 1 experiment. So this hypernuclei can decay into double lambda hypernuclei. So via this cascade nucleon to lambda-lambda conversion, then we can at the same time produce hydrogen-5 double lambda when we produce this hydrogen-7 cascade. And this also decay in weak interaction. And this is the goal of E75 experiment. So the key reaction to connect these two objects is this decay process of hydrogen-7 cascade into hydrogen-5 double lambda plus 2 neutrons. And this, namely, this E75 experiment will bridge these two objects, cascade hypernuclei and double lambda hypernuclei, with this cascade nucleon to cascade nucleon lambda lambda conversion. So let me explain a little bit about double lambda hypernuclei. So we plan to populate this hydrogen-5 double lambda. So this is very famous helium-6 double lambda observed in Nagara event. So we plan to populate this mass number 5 system, and many theoretical calculations support its existence of the resistance of this mass number 5 A45 isodoublet. And yes, and our purpose is to measure the mass of this hydrogen-5 double lambda by looking into the momentum of pion coming from the two-body decay of this double lambda hypernuclei. And then by using the technique of decay pion spectroscopy, so we can, in principle, we can determine the mass of this hypernucleus. So to do so, we are preparing a new cylindrical detector system with a solenoid magnet and the time projection chamber. So these are photo of solenoid magnet, and this is the time projection chamber. These two we borrowed from the LIPS Spring experiment group. And then I go back to the topic of cascade hypernucleus. So, okay, we are going to study this object. So it is composed of alpha and 2 neutrons and 1 cascade minus hyperon. So one of the interesting points in this hypernucleus is that it is very close to the onset of cascade binding. Actually, many calculations predict a bound state of hydrogen-7 cascade. I show next page. In contrast, for lighter hypernucleus, such as mass number 4 system, so this object might be bound or unbound. So it depends on the cascade nucleon spin-dependent, isospin-dependent interaction. So these two authors made a calculation, and the result is strongly depending on this cascade nucleon interaction. And according to Hiyama-san, this object is suited to study alpha cascade spin isospin independent interaction. And also the third feature is that this hypernucleus has maybe only one bound state, and there are no excited bound states, so that the level structure should be very simple. And okay, this is the calculation by Lee-san using the chiral effective field theory calculation. And okay, this is the result for hydrogen-7 cascade. The binding of 3.5 MeV with a very small decay width is predictive. And also the Hiyama-san made calculation using ESC04 or ND potential and interaction. And they, okay, this calculation gives a binding, positive binding with a larger width for ESC and smaller width for ND or Hall potential. So the question is that this bound state has a narrow width or not. So it's an open question, and we'd like to study about this width of this bound state. And the second feature of this object is that it has very limited number of decay modes. So according to this paper in 1996, it has only 4 decay modes. So this can be explained if we consider cascade hyperon is absorbed by this alpha core, and after the conversion or absorption, 1 proton and 2 neutrons and 2 lambdas are left after separating 1 proton from this alpha core, and there are 2 more neutrons. And due to this separation energy from alpha core. So the Q value would be very small after this conversion, and they are only whole decay mode with positive Q values. And according to calculation by Akai-san and Fuse-san, the branching ratio for the first decay mode is as large as 90%. And this one is a very recent paper by Oni-san and his colleagues. And they made an independent calculation with a theoretical, statistical model. And they gave a branching ratio into hydrogen 5 double lambda plus the neutron of about 50%, so that this decay branch should be very large. To do spectroscopy for hydrogen 7 cascade, we will make use of this K1.8 beam line together with this S2S spectrometer. The detail of this S2S spectrometer will be given maybe by Mr. Harada today, next session, or a presentation by Dr. Gogami tomorrow, plenary session. And we use this setup and changing the target from active fiber target for E70 target to lithium target. So we essentially the same setup. We can make a spectroscopy for this cascade hypernucleus. And okay, so this is the expected spectrum calculated by Hiyama-san and Koike-san, and this is theoretical spectrum. And if we take into account the experimental resolution of about 3.5 MeV, so this is our expectation. Okay, so this is a realistic resolution. So we would have some tape for EAC potential or ND potential, and for Hall QCD potential, we may have a peak structure in the bound region. So we plan to carry out 1 week measurement, and we expect to have, say, 56 to 104 events for this bound cascade hypernucleus. So this is our attempt to be done next year and to study this object. Let me summarize my talk. So today I mentioned this E75 experiment. We plan to investigate almost the lightest double-stranded nuclei, namely hydrogen 7 cascade and hydrogen 5 double lambda. So this hypernucleus will be the lightest cascade hypernuclei produced experimentally than ever. And probably it's very close to the onset of the binding. And the decay mode is very limited, and we plan to make use of this decay mode into hydrogen 5 2 lambda plus 2 neutron to produce this object. So we expect this resolution, and possibly we can improve the resolution by using a Sina target, and to possibly find this kind of spike structure in case of this Hall QCD potential. Thank you for your attention.
Thank you very much for nice talk. Now, please, questions or comments to this topic. Okay. So maybe some general question. When do you expect first results?
Maybe 2 or 3 years later.
Okay. Okay. So
we will do the experiment 2003 next year, maybe summer or so. It takes 1 year or so to conclude. Yeah, so maybe 2024 or possibly 25. We can show results.
Okay, okay. We wish you good luck, and we are looking forward to your results. So if there are no questions, so let us thanks again. And next talk is by Nanamura. He will talk about results about sigma plus proton. I'm sorry, is he Dr. Nanamura? Is he present here or? Sorry. So I misunderstood you first time. So Dr. Nanamura is also online, and he will talk about the results on sigma plus proton scattering from JLab experiment. Please.
Okay. Can you see my slide?
Yes, we
can
see
you hear
and
me?
hear you. We see your.
Okay. Okay, I'm Takuya Nonamura, Kyoto University student and belonging to JAEA Hadong group. I'm very glad to participate in this conference and talk our analysis results of sigma plus p scattering in the JPAC E40 experiment. JPAC E40 experiment is the experiment for measurement of differential cross sections of sigma p scatterings. And physics motivations are verification of repulsive force due to Quark Pauli effect in the sigma plus p channel and systematic study of the sigma n interaction. Isospin 3/2 sigma n channel is simply represented by 27 plate and 10 plate of flavor SU3 bases for the baryon-baryon interaction. Therefore, sigma plus p channel is the best channel to investigate 10 plate, whose triplet S1 state is predicted to have a strong repulsive force originating from the Pauli effect at a Quark level, called Quark Pauli effect. Main purpose of the experiment is measurement of differential cross section with high statistics for sigma minus p elastic scattering and sigma minus p to lambda n in elastic scattering with sigma minus production data, and sigma plus p elastic scattering with sigma plus production data. I focus on the sigma plus channel in this presentation. Additionally, we tried to establish method to measure pi minus p to k0 lambda reaction. Sakao-san will talk about this. Sakao-san will talk in the next session. Okay, generally, hyperon-nucleon scattering experiment is difficult due to short lifetime of hyperons. Previous sigma plus p scattering experiments could identify only a few tenths of events. In our experiment, to produce and tag large amount of incident sigma particles, we use high-rate pion beam and large acceptance spectrometer. Using liquid hydrogen target and surrounding detector system, we can reconstruct reactions from two-body kinematics and detect the recoil protons with large acceptance. Experiment was performed at K1.8 beamline in JPAC Hadron experimental facility. This is the experimental concept of the JPAC E40 experiment. Both the sigma production reaction and sigma p scattering were occurred in the liquid hydrogen target. In order to identify the sigma plus p scattering events, momentum of incident sigma plus and the recoil protons kinetic energy and recoil angle should be measured. This is the experimental setup. Sigma plus production reaction was analyzed by the two spectrometers, K1.8 spectrometer and Kramer spectrometer. Charged particles involved in the sigma-induced reaction, such as the recoil proton of sigma p scattering, were measured with the surrounding detector system, so-called catch system. Catch system has a cylindrical fiber tracker and BGO calorimeter, so we can get information on particle directions and energy of protons. First, I'll show analysis of sigma production reaction. Momentum of pi plus beam is reconstructed by the K1.8 beamline spectrometer using third-order transfer matrix method. Momentum distribution of pion beam is like this. For scattering particles, momentum and path length are analyzed with Kramer spectrometer by Runge-Kutta method. Using momentum and mass information, we can select scattered K+. For selected pi K reaction, missing mass was calculated. In missing mass spectrum, we can see clear sigma plus peak. Approximately 49 mega sigma plus production events were identified. And as the missing momentum of pi-k reaction, momentum of sigma plus can be determined. It is also incident momentum for the sigma plus p scattering. In the sigma p scattering analysis, the sigma plus events were categorized into 3 by momentum ranges: low momentum region, and middle momentum region, and high momentum region. Next, I'll show analysis of catch system. Using cylindrical fiber tracker, trajectories of charged particles are reconstructed. And for particle identification, we use energy loss correlation between fiber tracker and VGO calorimeter for each track. We can see 3 loci. This is proton locus, and this is pion stopped in VGO. And the last is pions penetrated VGO. From this correlation, protons are well distinguished, and kinetic energy of a proton are fully measured by VGO calorimeter. Combining the analysis of the spectrometers and catch, we can identify sigma plus p scattering events by checking a kinematical consistency for the recoil proton. Here, events with 1 proton in final state are severely contaminated by sigma plus to p pi 0 decay. Therefore, we concentrate on events with 2 protons in final state. For sigma plus p scattering, sigma plus scattering followed by sigma plus to p pi 0 decay case is corresponding. The kinematical consistency check is performed by comparing measured and calculated energy for the recoil proton. We can calculate the kinetic energy of the recoil proton from incident sigma momentum and recoil angle of proton. At the same time, the kinetic energy of the recoil proton was directly measured using catch. So, for the sigma plus p scattering events, the difference of the measured and calculated energy defined as delta E distribute around 0. This is the delta E distribution after applying cuts to select sigma plus p scattering events. Cut conditions were decided using information on reconstructed vertex position and distances between tracks and kinematical consistencies for decay proton, and so on. In total, approximately 2,400 sigma plus p scattering events were identified. This is 80 times more than past KEK experiments. Differential cross-sections were derived from approximately 2,400 sigma plus p scattering events. The data quality has been significantly improved. The error is less than 20%, and angular step is fine. Delta cosine theta is 0.1. Systematic error mainly came from the uncertainty of the background estimation and efficiency for low momentum proton. In comparison to theoretical models, our results were not as large as the differential cross-sections predicted by FSS and FSS2 models. These models are based on the co-cluster model in the short-range region. On the other hand, ESC08 and NSC97F are consistent to some extent. Note that NSC97F agrees well with our data in terms of the differential cross-sections, but it predicts an attractive sigma plus p interaction it doesn't agree with the current common understanding of sigma n interaction. Extracting the contribution of the triplet S1 state is very important to study the recursive nature of sigma plus p system due to the clock Pauli effect. Therefore, we tried phase shift analysis, referring to formalism of NN scattering. The differential cross-section was calculated as a function of phase shifts. We considered contribution by the wave, specific formulas for the differential cross-section I0, and matrix elements are like this. The function representing differential cross-section has 11 phase shift parameters. We categorize these phase shift parameters in terms of multiplets of Frey-by-SU3 symmetry, 27 plate or 10 plate. The phase shifts for singlet even and triplet odd states are well constrained from PP data, and the difference between the theoretical predictions is small. Therefore, we fix these phase shifts as a constant. The phase shifts for triplet even and singlet odd states are unique to the sigma plus p channel and should be determined from the fitting. However, 6 parameters are still too much to perform meaningful fitting. For present momentum range, theoretical uncertainty of triplet D is relatively small. Therefore, only phase shifts of triplet S1 and singlet P1 states were treated as free parameters. The effect of the uncertainty of fixed phase shifts was examined using different sets of fixed parameters, which are taken from PP scattering based on complete SU3 symmetry or Nijmegen models. Note that the sign of the phase shifts of triplet S1 states cannot be determined by this fitting method, and positive and negative. This is a negative triplet S1 phase shift case, and fixed phase shifts are taken from ESC 16. Obtained phase shifts of triplet S1 and singlet P1 states are shown. Phase shift of triplet S1 states is well determined and consistent with ESC 16 or NSC 97F. Error is less than 5 degrees. If the sign is assumed to be negative, this result suggests that the repulsive force is moderate. In contrast, the phase shift of singlet P1 state deviate considerably depending on the fixed parameters. Although they are ambiguous, this result may support the prediction of the FSS2, ESC 16, and NSC 97F, in which the interaction of singlet P1 channel is weakly attractive. Okay, I think the time is over, so I just show the summary page. Thank you.
Thank you very much for nice talk. Now the paper is open for questions. Please, Laura.
Hi, very nice talk. Laura here speaking. Can you go to slides number 15, so the previous one? I did not understand how you can, yes, thank you, how you can get negative and positive phase shifts at the same time. And because, I mean, very naively, I would imagine that you can decide between the sign. Maybe can you explain this to me again?
Numerically, positive case, positive triplet S1, phase shift of triplet S1 states. can be both can be positive and negative. It's depend on the initial value of fitting. So we believe the phase shift of triplet S1 state is negative, but we examined both cases.
Okay, so if I understand correctly, it is model dependent, basically. So the fact that you have negative and positive results.
Okay. So, some other question, or if not, let us thanks again. And now we will continue with presentation in person. Yeah, okay. Yeah. So it is Dr. Ishigawa, and he will talk about a high resolution spectroscopy of the sigma N curves at J-Park.
Oh, so I was assigned to be online, right?
No, the slides are not there. Not uploaded.
Okay.
Slides.
Oh, so I registered not the local, so not online, but maybe so. Okay, thank you. So thank you very much. So I'm Yuda Ichikawa from JA. So at first I'd like to thank to give me a chance to talk this theme in this conference. So recently, so in the last PhD, so the last PhD of JPERC, so we submit the new proposal to measure the sigma and cusp with a really good resolution. So we in this talk, so I will talk about this new experiment detail. So okay, I would like to start from what is the sigma and cusp. So this is how the lambda p invariant mass spectrum or equivalent spectrum of the pp reaction or k minus d reaction or pi plus d reaction. As you can see, that there is a clear enhancement near the sigma minus threshold, which corresponding to 2.13 GeV over c square. So like this. So this clear enhancement is called as a sigma and cusp. So in JPERC, in 27 experiment also measure the sigma and cusp via the inclusive d pi plus k plus reaction. And recently, and in this conference, there are a lot of slides to show this slide as Alice femtoscopy, but the Alice lambda p femtoscopy also measure the clear enhancement due to the sigma and cusp like this. So as you can see, there are a lot of the measurement about the sigma and cusp. However, the origin of the sigma and cusp has not been determined yet, especially whether there exists a two-body bound state of the sigma and system exists or not had not been determined. Okay, then this is the purpose of the E19 experiment. So in this experiment, we aim to deduce the sigma and scattering length with this isospin and spin channel by fitting the sigma and cusp spectrum shape observed in the missing mass of the dk minus pi minus reaction. Then we will investigate whether exists an unstable bound state as a sigma and divariant or virtual state. The key of this experiment is an excellent missing mass resolution thanks to the S2S spectrometer and high statistic. And the detail of the S2S spectrometer will talked by Gogami by tomorrow. And we will be able to achieve the best resolution of 0.4 MeV in sigma, which is 2 times better than the past experiment, which achieved by Harris experiment at COSY. Okay, then let's move on to what is sigma and threshold cusp. Okay, let's consider the A going to B, C, D reaction. So, okay, when we look at due to the intermediate B prime, C prime to B, C, S wave risk scattering, so the threshold curves possibly appear. So here, the reaction rate or spectrum shape above the threshold and below the threshold can be described as like this. So here, K shows the relative momentum for the B prime C prime system, and small a and small b corresponding to the real part and imaginary part of the scattering length for B prime C prime system. So as you can see, the spectrum shape can be described as a function of the scattering length. So here I demonstrate this formula. So here I fix the imaginary part to be 2.0 centimeters. So then we vary the real part like this. So then, as you can see, there is a clear difference. So due to the difference of the real part, especially below the threshold, and here, so we fix the real part to be 1.0, and we change the imaginary part like this. So there is also the difference. So then, as you can see, the spectrum shape strongly depending on the scattering length. So in other words, we can, by measuring the spectrum shape near the threshold region precisely, then we can deduce the scattering length itself from the spectrum. Okay, then let's move on the sigma and cusp itself. And sigma and cusp can be expressed by the sigma and scattering length of scattering length. But the important point is we can dedicate a specific isospin and spin channel. So okay, for the isospin, the sigma and system have two possibilities, namely the 3/2 or 1/2. But the measured final state should be lambda p. Then the total spin of the sigma and cusp should be 1/2. And for the spin, there is also two possibilities, spin singlet or triplet, but we can say the spin triplet is favored because we will use this reaction and we will measure the very forward pi minus event. So then the spin flip amplitude of this reaction should be negligible. Then the spin configuration should be followed the deuteron target spin configuration. So then we can say the spin triplet is favored. So then finally we can say the sigma and cusp can be expressed by the sigma and scattering length of the isospin 1/2 and the spin triplet channel. Okay, then I will list up the requirement for the new experiment, requirement for the sigma and cusp experiment. Okay, so we need a good energy resolution and high statistic and good signal to noise ratio. It may be some kind of a common issue, but the important point is to avoid the final state interaction except for the sigma and system. So here, the reaction diagram to produce the sigma and cusp is shown. So as I showed in the previous slide, the intermediate sigma n to lambda p descattering, the sigma and cusp is created. But in case of the stopped K- reaction, the momentum of the pi minus and lambda and proton is almost same. Then the final state interaction effect of the pi lambda and pi proton and the yn should be equivalent. Here, please note that the final state interaction of the yn system should be the signal of the sigma and cusp, but the pi lambda or pi p final state interaction should be the background. So it can possibly distort the original sigma and cusp spectrum. So here I show the old bubble chamber experiment of the stopped K- reaction. So here the invariant mass spectrum of the pi lambda system, the clear enhancement, the sigma 38.5 is measured like this. So then we can say the final interaction effect of the pi lambda is really large for the stopped K- reaction. On the other hand, in case of the in-flight reaction, so the incident kaon and pions momentum is order of 1 GeV over c. But in case of the momentum lambda and proton, it's order of 200 MeV/c or something. It's lower. And due to this momentum mismatching, so we can neglect the final interaction of the pi lambda or pi p for the in-flight reaction. So in other words, we can say that we can assume the impulse approximation for the in-flight reaction. And the other important point is to decompose the spin singlet and spin triplet contribution. So in case of our experiment, we will use this K- d going to lambda p minus reaction. Then we can extract only the spin triplet contribution by following the deuteron target property. But I showed a lot requirement for the sigma and cusp, but there was no experiment to satisfy their requirement. Okay, I show some summary of the past experiment. There are the old bubble chamber experiment, Brown, Eastwood, Tang, and Brown Institute have used the in-flight K- dk minus pi minus reaction, but their statistic is low and resolution is not so good. And Tang, experiment is much higher statistic and the resolution is better, but they use the stop to K minus reaction. And there is also the counter experiment by using this reaction, but this experiment resolution is really poor. Here the PP reaction and the Alice pentoscopy is a kind of the recent experiment, and especially the Koji-Harris experiment is important because they achieve the best resolution of 0.8 MeV, this one. So they could achieve the best resolution. However, the signal to noise ratio is not so good, and in case of the PP and pentoscopy, there is no guideline to decompose a spin configuration. So it means that both singlet and triplet are mixed together. And also the PP reaction, the complicated reaction mechanism via the N star or delta star is known. And we need to, they need a partial analysis with spin observable to make it clear, the reaction mechanism. And also, of course, the Alice experiment is really good, and the clear enhancement is seen, but in case of the pentoscopy, the spin singlet and triplet are mixed. And further experiment by measuring the spin observable may be the competitor of the our E90 experiment. Okay, then I will show about the E90 setup. So we will use the K minus D going to lambda P minus at 1.4 GB over C, and we will measure the beam K minus with beamline spectrometer, and we will measure the outgoing pi minus by using the S2S spectrometer. And both beamline and the S2S spectrometer have a really good momentum resolution. Then finally we can get a good mass resolution about 0.4 MeV in sigma. Yeah, and in order to suppress the final state, in order to restrict the final state as the lambda P, and in order to suppress the background reaction, we additionally install the hype TPC detector like this. And the detail of the hype TPC detector will be talked about talked by Shuhei Hayakawa in today's talk. Okay, so last I will talk about the key of the E90 experiment. Really, the high resolution is really important. Here I summarize the theoretical value of the sigma scattering length with isospin 1/2 and spin triplet. This is the theoretical value. So again, the small a corresponding to be the real part and small b corresponding to the imaginary part. And here I summarize the value for the meson exchange model and also the chiral EFT model for each cutoff value. As you can see, especially the real part is widely distributed. So from 2.6 femtometer plus 2 plus 3.83 femtometer. Here, A is negative corresponding to the attractive force, and A is negative case. It should be the bound state. There exists a bound state. Anyway, there is a large ambiguity of the sigma scattering length. And also, and I demonstrate the spectrum shape of the sigma cusp. And by following this scattering length value, I show the sigma cusp spectrum with ideal case by the solid line. So it means solid line case is a calculated spectrum without any statistical effect or some resolution effect. So, but the point with error bar shows with a statistical effect and the resolution effect. Here, I assume the resolution about 2 MeV, which corresponds to the past experiment. So as you can see, there's a clear difference in between the ideal distribution solid line and the point with the error bar. So, but in case of our resolution 0.4 MeV, the solid line and the point with the error bar, so it means with and without statistical and resolution effect is almost comparable. So then by measuring the sigma cusp with really good mass resolution about 0.4 MeV, we can discuss the scattering length of the sigma system. Okay, I summarize my talk. The sigma interaction is a really important key of the octet baryon interaction and lambda and sigma hypernuclear. And the sigma cusp can be expressed by the sigma interaction, especially sigma scattering length. And there are a lot of past experiments to measure the sigma cusp. However, the origin of the sigma cusp remains unclear yet, especially whether exists the sigma diabaryon or not has not been determined yet. So infinite decay minus pi minus reaction has an advantage to dedicate a specific isospin and spin channel. And the E19 experiment will investigate the nature of the sigma and cusp with the world-best quality. We will use a K1 point beamline spectrometer and SCS for the pi minus measurement, and HYPE TPC will be installed for the background suppression. And we estimate 1.4 times 10 to 4 sigma and cusp event in the 15 days beam time, and 0.4 MeV sigma mass resolution will be achieved, which is 2 times better than the past experiment. And we can deduce the scattering length with a statistical error less than the 0.3 femtometer. Okay, thank you.
Thank you very much for your nice talk. Now time is for question.
If you see a clean cusp, that the cusp is clean, what you can conclude is that the interaction in S-wave is attractive, but not enough to bind. That, I mean, is quite...
It's depending on the results. So.
Yes, I mean, if it is right, with a clean cusp, as you see there, the interaction is attractive in S-wave, but not enough to bind the state. That is a theorem.
I'm not sure. So then the the colorability model also predicts some kind of the bound state. So anyway, it depends on the result, experimental result, I think.
Okay. Another question?
Actually, in the Dalitz model, there could be a cusp, even if there is an unstable bound state. Yeah, such case is introduced by the Dalitz. Yeah, it is the Dalitz paper. Yeah, that's usual, but because of the form factor part he introduced, there could be a cusp even if there is a unstable bound state. This is the Dalitz paper.
Anyway, by following the previous helium for sigma, so this isospin-spin interaction should be really attractive and should be the key to produce a helium for sigma. So then maybe the interaction of this isospin-spin, so it's measured channel, it should be really important.
Okay. So, short question, please.
Thank you, your talk. And when the scattering length, real part of the scattering length is negative, then we may have a bound state, but it is just repulsive. In the case of the sigma n potential, then the Cook-Parry effect is effective. Therefore, many of the chiral FT results having the negative scattering length of the imaginary part may show that it is just repulsive and there is no bound state. As found there is no peak in the bound state region from many of the calculations. Then what do you think of it?
Yeah, maybe important point is the relation with the effective range, right? So by comparing the effective range and the scattering length, we can discuss whether it is bound or repulsive, I think. Maybe the further study may be important, so I'm not sure we can say something, but yeah.
Okay, thank you once again. We will continue with another online lecture. Okay, it will be Dr. Tokiyasu, and he will talk on spectroscopic study of 10 Keiksei lithium hypernucleus with K minus K plus reaction. Please. Can we?
Yes, thank you, Mr. Chair.
Yeah.
Do you hear me?
Okay.
Okay, thank you. Okay, I'll start. Hi, I'm Atsushi Tokiyasu. I'll talk on this title. Okay. Let me start from the introduction. Understanding of the baryon-baryon interaction is one of the main topics of nuclear physics. In S equals 0 sector, a large amount of nucleon-nucleon scattering experimental data can be used to extract the interaction between the nucleons. On the other hand, in S equals -1 sector, due to the short lifetime of hyperon, the spectroscopy of the hypernuclei is the study of the interaction between hyperon and nucleon. And recently, high statistics hypernucleon scattering experiment was performed and great results are reported elsewhere during this conference. And in S equal -2 sector, the interaction between lambda and lambda, or Xi and nucleon, can be studied via the investigation of double lambda hypernuclei or Xi hypernuclei. However, compared to the S equal -1 sector, the experimental data of such nuclei are limited so far. So therefore, we are trying to open the S equal -2 frontier at JPAC K1.8 beamline in Japan, where we can use the high intensity and high purity K- beam. Okay, in this page, a series of projects related to Xi hypernuclei at JPAC are summarized. And the ESO7 experiment, which is a merging experiment, was performed, and some carbon-15 Xi events were observed. And the ESO5 experiment using the SKS spectrometer was performed, and the consistent result with the previous experiment KK or BNL were obtained. And in this experiment, the existence of the barium-12 Xi was indicated. And this experiment is an upgrade experiment of ESO5, and E7T experiment is now ongoing in JPAC. And for this experiment, newly constructed S2S spectrometer will be used. And another experiment, E75 experiment is also proposed. In this experiment, lithium-7 target will be used to produce the hydrogen-7 Xi. And after this experiment has been done, a systematic study by using various targets will be necessary to further the research of Xi hypernuclei. So among a number of targets, we are trying to take data using the boron-10 target, because by using this target, lithium-10 Xi will be produced. Okay. So in this slide, I'd like to talk why lithium-10 Xi is interesting. This importance has been already mentioned in the excellent review talk by Hiyama-san as the first session, but let me repeat briefly here. And lithium-10 Xi hypernucleus can be interpreted to have the component of 2 alpha particles and 1 Xi particle and 1 neutron. And the interaction between the alpha and Xi can be determined by the investigation of H7 Xi. And in addition to that, Xi and neutron interaction can be extracted by studying the lithium-10 Xi. And these figures shows the phase shift of S5 Xi-N interaction. In the ESC model, spin triplet is strongly attractive. On the other hand, in the HAL QCD, triplet is weakly attractive. And this difference might play an important role for calculating the binding energy or level ordering and so on of this system. Okay, so these figures show the calculated binding energy of lithium-10 Xi based on ESC and Nam-Hen-D model. And in addition to that, preliminary calculation result based on HAL QCD was reported by Hiyama-san at the first session. And the calculated value of the conversion width vary from model to model, but all calculation results predict the existence of the bound state. And the binding energies are large enough to observe the peak structure in the experiment using S2S magnet, which missing mass resolution is less than 3 MeV. And we can say the measurement of binding energy of our gamma width or the level ordering of this system is useful to check the validity of the theories. Okay, and this is a schematic view of the experimental setup. K- beam is injected to the target located here, and the momentum of the K- is analyzed with K1.8 beam line spectrometer. The resolution of this spectrometer is 3.3 times 10 to minus 4 in FWHM. And the scattered K plus is detected by this S2S spectrometer with a resolution of 6.0 times 10 to the minus 4 in FWHM. And by using this system, we can perform the missing mass spectroscopy with the mass resolution of less than 3 MeV. in FWHM. As for the detail about this system, Gokami-san will talk at the last session. And the most important thing to consider when conducting the experiment is its yield. The yield is expressed by this equation, a number of beam times number of targets and differential cross-section times experimental acceptance. The cross-section of the Xi hypernucleus is the order of 10 nanobar, and the acceptance of the S2S spectrometer is 55 millimeters radian. And so it is corresponding that we can see the 100 events of Xi hypernuclei if we use the 10-gram target and the beam time is 20 days at JPark. And we cannot control this differential cross-section. And to increase the statistics, we need a high luminosity K- beam or long beam time. But these are the strongly coupling to the facility situation or budget, so it is very difficult to change this. So what can we do as an experimenter is to increase the thickness of target. However, if the target thickness is larger, the missing mass resolution worse. So therefore, in ESWD experiments, an active target system will be used to compensate the energy loss inside the target. And in E55 experiment, decay pion spectroscopy will be applied. And in addition to this, in this talk, I'd like to propose a semi-exclusive method. Okay, the missing mass resolution can be written by this equation, and which can be divided into two parts. And these parts comes from the S2S spectrometer and kinematics, and the values are approximately 1.8 MeV. And if we would like to achieve missing mass resolution less than 3 MeV in total, this term, which comes from the target energy struggling inside target, is less than 2.5 MeV. And left figure shows the energy deposit of K plus inside the boron target, depending on the thickness. And in case that the thickness is 40 millimeter, the struggling of energy is 2.0 MeV. So this is a limit of the target thickness. However, to use this target of this thickness, we should correct the mean energy loss by Bethe formula. For that, we should reconstruct the vertex point within the resolution of 1 millimeter. Okay, so this slide shows the conceptual setup near the target system. Our target is segmented, and the tracking system will be installed surrounding the target. And as a tracking detector, SST or DSST will be used. And for the particle identification, scintillation counters will be used. And the pions from the decay of the hypernuclei are detected with this system and used for the reconstruction of the vertex point with a combination of the K minus or K plus and pi minus. And then the segment in which the event happened is identified. And by calculation, the energy loss of K minus and K plus are corrected. The vertex resolution of K minus and K plus is estimated to approximately 5 millimeter. It is not enough. But on the other hand, if we use a pi minus for the tracking reconstruction, the vertex resolution achieves less than 1.0 meter. Okay, so the important point of this method is that the pion used for the tracking system from any decay mode, we don't mind what decay mode. So in this sense, we can say this measurement is semi-exclusive. So lithium-10 Xi has more than 35 decay modes, like the double lambda hypernuclear or tree hypernuclear and so on. And it's difficult to estimate the efficiency of this method for each decay mode. Then I checked the feasibility with a very simple assumption. Okay, so finally I show so lithium-10 Xi produced via this reaction with a beam momentum of 1.8 GeV over C. And I assume the Xi-N pair inside the Xi hypernuclei decay into 2 free lambdas. And here, momentum Xi-N is calculated following the ratio of the mass. And based on this assumption, I generated the events by Gent4, which is a Monte Carlo simulation code. These are the just figures events of the event displays. And by this study, the efficiency to select the correct vertex is estimated to be approximately 30%. And the reasons why reconstruction fails are, for example, the neutron decay mode of lambda, or multiple scattering of pion inside the target, or a pion from the other source, for example, is a proton, nuclear scattering, and so on. Okay, so this is a summary. Okay, so I will skip this slide. Thank you so much for your attention.
Thank you very much for your nice talk. Now the paper is open for questions, please. Okay. No questions. So everything is clear, seems to be so. So if there are no questions, thank you once again for your talk, and we wish you good luck with experiment.
Thank you.
Now, we will continue now with theoretical talk by Dalibor Skoupil from Nuclear Physics Institute in Řeš. He will talk about the isobar model for electroproduction of K plus sigma minus. Okay. So please.
So hello everyone. First of all, let me say that I'm very pleased that there are so many people interested in photo production. That's very nice. So for a very long time we have been interested in K plus lambda photo production, but recently we switched to a different channel. We studied K plus sigma minus photo production within our isobar model. And this talk will serve as a kind of brief introduction or brief overview of what we have recently done. Okay, first of all, let me say something about the motivation. So our motivation is to understand the baryon spectrum and the production dynamics of particles with non-zero strangeness at low energies. We know that there is a constituent quark model which predicts far more excited states of a nucleon that was observed, for example, in pion or eta production experiments. This is a so-called missing resonance problem, which we have to deal with. We know that our further step will be to use our models for some hypernuclear physics calculations. And the models, which are, for example, the isobar model I will introduce today, or reciprocal resonance models, are a good tool to use for hypernuclear physics calculations. There are now plenty of really good quality photo production data from several collaborations, particularly from class collaboration which provided us with many thousand data. And now let's move to introducing the model. So our model is the isobar model, and this model is a single channel approximation, which basically means that we do not take into account any higher order contributions like rescattering or interaction in final state. But these contributions are kind of included by means of effective values of coupling constants, which are then adjusted to experimental data. We use the effective hadron Lagrangian, and that means that we introduce hadrons either in the ground or excited states, and the amplitude is then constructed as a sum of Feynman diagrams on a tree level. We can basically divide the Feynman diagrams into two broad classes. The first part is background part, which is made of Born terms in the ST and U channel with exchanges of proton, kaon, and lambda respectively, and non-Born Feynman diagrams in the T and the U channel with exchanges of K, kaon resonance and hyper resonance respectively. The only diagram which creates any shape in the cross-section is the non-Born S channel diagram of exchanges of nuclear resonances. In this model, we have quite a few free parameters, which then have to be adjusted to experimental data. And actually, this is kind of an issue because we still fight with adjusting the parameters, like not overfitting the data, not underfitting. And this will be a kind of focus of this talk. And so this model gives us a good agreement with data from the threshold of 1.6 GeV to, let's say, 2.5 GeV. Recently, we have implemented some new features into our isobar model. So nowadays, we can exchange high-spin resonance states, like nuclear resonances with spin 3/2 or 5/2, and hyper resonances with spin 3/2. We have also thought about the restoration of unitarity, and because of this, we have implemented energy-dependent widths of nuclear resonances. And even though this is beyond the scope of this talk, we have also extended our description from photoproduction to electroproduction. Okay, now let's go to the K plus sigma minus channel. So after introducing the model, I told you we have to go through a fitting procedure. So first of all, we have to select the appropriate, let's say, ingredients. So for the non-resonant part, there are bond terms and exchanges of Coulomb particles in D channel and sigma ions in VU channel. And the resonant part then consists of exchanges of nuclear resonances, and when we deal with sigma production, we have to take into account also delta resonances in the S channel. So we used around 600 data points to fit approximately 25 free parameters of our model. The main coupling was taken from the K plus lambda channel, and then actually we went through a fitting procedure and we arrived at two results. The first result, which we call fit M, was achieved by minuit only. And in this fit, whose chi-square is 2.3, in this fit we have 25 free parameters and 14 resonances. Actually, then we thought more about the fitting procedure, and thanks to our colleague Dimitris Peteris, we introduced some, I would say, enhanced method for fitting the parameters. And we arrived at another result with chi-square a bit higher, but on the other hand, this fit gives us far less free parameters, just 17, and far less resonances. So instead of 14 resonances in fit M, we have now just 9 resonances in fit L. So the main important things about the models is that we include just one delta resonance in order to get a good description. There are no hyperresonances needed for good data description. And we have a quite of good agreement with cross-section beam asymmetry data, which we fitted, so it is no wonder actually. But I think the most important part is that fit L produces a very economical fit. So now let's see the table of the included resonances. You see that we include Coulomb resonances, nuclear resonances, delta resonances, and sigma resonances in our analysis, but in the results, in the fit M, there is just one, if I can use it, yes, there is just one delta resonance. In fit L, there are no delta resonances. And actually in the fit L, we have just one Coulomb resonance, which is kind of unusual because in our models we usually have two resonances because of their interference and importance for data description. Here you can see differential cross-section which depend on the photon lap energy. The photon lap energy goes from a threshold up to approximately 3.5 GeV, and it is plotted for several Coulomb angle bins. The red curve is fit L, the one with the enhanced fitting method, and the fit M is denoted by a blue curve. You can see that both of these fits can quite nicely reproduce the data. Just fit L creates more shapes in the forward angles. Now this is just fit M, and I show it how it reproduces the data once we omit some resonances. So we see that the most important ingredient is the N3 resonance. Once we omit this resonance, we get a much higher cross-section than what we observe at the threshold area. And then actually also the N7 resonance is quite important. There is also some importance coming from the delta resonance, but it is not that tangible. This is the same figure, but this time for fit L. And you see again the N7 is quite important when once we omit this resonance in the backward angles, the cross-section goes up quite significantly, whereas in the forward angles, we cannot describe the data at the threshold. And there is also one more important ingredient coming from M4, which is a spin 5/2 nuclear resonance, denoted by the green curve. And again, when we omit this resonance, we cannot describe data in the forward angles and higher energies. Now these are beam asymmetries, independence on account center of mass angle. for 6 energy bins. You can see that fit L and fit M both describe the data quite well, and they differ just at high energies and backward angles. Again, what are the important ingredients for fit M? We identify the nuclear resonance N7 as the most important ingredient, because once we omit this resonance, the beam asymmetry in several bins changes its sign. And for fit L, it is quite similar, but the importance of the nuclear resonance N7 is not so tangible. Here I show you the differential cross sections independence on both energy and Cowan angle, because I really like these 3D plots. It lets you know how it behaves, and you can get some feeling. So I think you still have in mind the table where I showed the resonances included in fit M and resonances included in fit L. And so in fit L, we basically include the same resonances which are in fit M, but there are a few less. And you can see that even though the included resonances are basically the same, we can produce quite different cross sections. The fit M produces one broad peak, and then it kind of diverges at forward angles, whereas the fit L produces also a second peak somewhere around 2.4 GeV. So I would like to stress that even though we have less resonances in fit L, there are still important some interference terms which then create these shapes. Okay, so the analysis of K plus sigma minus was a kind of first step in our journey in analyzing all sigma projection channels. So this is kind of outlook, and this process will be a kind of 3-step process. So first of all, we need to derive all scalar amplitudes for all channels involved. Then we use SU2 isospin symmetry in strong vertex, because with help of this symmetry we can relate the couplings from different channels, and we use also helicity amplitudes in electromagnetic couplings. Again, we have to feed the data, but our first thought would be to basically emphasize the K plus sigma 0 channel, because this channel is dominated by data. Approximately 90% of sigma for approximation data is focused in this channel. And then we can use minuit, we can use regularization methods, we can use SU2 isospin symmetry and helicity amplitudes to basically relay the couplings which are fitted to K plus sigma 0. So now let me summarize my talk. I told you about our recent development that we basically extended our models from K plus lambda channel to K plus sigma minus channel. What is important to say is that we need just one delta resonance and no hyperon resonances to get a nice data description. And I think the most important thing is to say that we upgraded the fitting method by adding some regularization techniques, and we have arrived at very economical fit, because I think this is one of the crucial things to disentangle the nuclear resonances, and not only nuclear resonances which contribute to the process. So thank you for attention.
Thank you, Dalibor, for your talk. Now, questions, please, or comments, please.
Yeah, thank you for your talk. I understand, like, in your motivation here, you're more interested in the S-channel resonances, right? Because you're looking for N-stars. But you also have the T and U channel contributions in your model. So could you extend this model to much higher photon energies, say 8, 9, 10 GeV, where you don't expect any S-channel resonances, but T and U to dominate? And could you then make a statement about the involved exchange mechanisms that play a role?
Well, actually, if you talk about 8 or 10 GeV, then we have to switch to a different model, because the isobar model doesn't give good description of data at these energies. We have done these things, but with a different model, a so-called Regge plus resonance model, where the background is described by Regge trajectories, in our case by Cowan Regge trajectories. And then basically in the resonance region, in order to get a description of the data, because in the resonance region there are some shapes which we need to describe, and we describe it by adding the S-channel nuclear resonances. But it is really, we have to really go for a different model in order to talk about these energies.
Okay, thank you.
Okay, other questions or comments? Okay, if not, let us thanks again. And the last talk of this session is by Franco Garibaldi from Rome, and he will talk about electroproduction of the lead target.
Okay, so let's talk about this experiment. This is one of the 3 experiments approved for the Jefferson Lab Paper Nuclear Collaboration, as underlined this morning by Satoshi Nakamura. The main focus of this experiment, among others, is the helping solving the Hyperon puzzle. Okay, we have already, of course, from Keon probe, we have already data on LED, but we will show that you need better resolution, better performance, as I will show. So, okay, let's remind what is the Hyperon pulse, Hyperon puzzle. Neutron stars are remnants of the gravitational collapse of massive stars having masses of 1 to 2 solar masses. They are, so the excellent observatory is to test fundamental properties of nuclear matter under extreme conditions. So we know that hyperons are expected to appear in their core at a certain density when the chemical potential is large enough to make the conversion of neutron to Y energetically favorable. But the relief of Fermi pressure makes, due to this appearance, makes equation of test stiffer with the reduction of mass that is incompatible with the experimental data. Okay, let's explain better. These sort constraint models, of course, you need you have to have different experiments at different masses. We have done in the past in Jefferson Lab carbon, oxygen, lithium, etc. And then we have planned these 3 experiments now. So as we will see in a moment, what seems to be clear that we need a repulsion necessary to reproduce the limiting value of lambda banking energy, and you can see from this calculation made by Vidania that in principle you can also disentangle which is the best NN lambda. So okay, so you have to choose the right one, the right lambda NN. So showing this from calculation by simulation calculation by Monte Carlo, by Leonardoni and others, it shows that if you put the right lambda NN force, you approach the right mass. Okay, the same behavior is with this calculation by G-matrix by Yamamoto, I believe. Okay, we are going to use, of course, the electromagnetic probe that, okay, you can see here what are the difference, the difference and the compatibility of the different probes, and you see that, of course, you excite different states with different probes, and you excite, for example, mirror nuclei with the electromagnetic probe. But the main characteristic of at least up to now of the electromagnetic probe is to have much better energy resolution. That is essential tool for spectroscopy. Okay. The spectroscopy is the only method that can measure the absolute binding energy from ground and excited states with an accuracy of about 50-70 keV. But what is important, is characteristic of a magnetic probe is that you need any calibration. It's a very important factor. This is a special characteristics of electromagnetic probe. So what this proposal experiment is to extend the study to the maximum, so to LED. We will see why LED has a particular role in this. And as also said by Nakamura this morning, this is a complementary to the other experiments we are going to do on calcium 40, calcium 48, and because this will allow us to extract isospin dependence of three-body lambda and force. So we know that the three-body forces are strongly A-dependent, so this makes the LED the best target to study the lambda interaction in a uniform nuclear medium with large neutron excess. We know that the contribution of the nuclear forces, which is known to be large and repulsive in nuclear matter at equilibrium density, is believed to be much smaller and negative in calcium with respect to LED. This is another mode. Okay, which is the lateral framework? Okay, there are different theoreticians involved, and okay, the framework has been suggested by Omar Benar. We did that at NICEF in the past, also in other laboratory, but at NICEF we did experiments in E'P in LED. And in any case, this is important to use this technique because you will see that missing energy spectra measured in A''P provide the baseline for a model-independent determination of hyperon binding energies. And this is very important, as you understand. So we know that the understanding of nuclear interaction involving hyperons is far from being complete. And the reason is a combination of incomplete knowledge of the process, the forces governing the system, and also in the concurrent use of approximation, theoretical many-body techniques. So using the PP target will allow us to investigate the hypernuclear dynamics in a new environment in which the three-body interactions are expected to play an important role. This will allow us, as said, to help solving the hyperon puzzle. Okay, as said at the beginning, the three-body force could provide the additional repulsing needed to make equation of state stiffer. Okay, let's see why, in particular, why the LED is the ideal nucleus for this business. Because this, all the measurements from the 80s from Saclay shows that the charge density distribution shows that the region of nearly constant density accounts for a very large fraction of the nuclear property. So this reflects that this is uniform matter in the neutron star. The same. The validity of this conjecture, I said we did the experiments. I will show in a moment some interpretation. We did these experiments at NICEF in the late 90s with the same kind of target that we'll use at Jefferson Lab. So you can see here that the short challenge correlations appear to be the most important mechanism leading to the observed quenching of the spectroscopy factor, while surface and shell effects only play an important role in the vicinity of Fermi surface. This means that deeply bound protons in the LED 208 ground state are largely unaffected by finite size and shell effect. So they behave as if they were in nuclear matter, this is the reason to choose this. So as underlined, this is also very important, hyperon binding energy, again, by the difference between the missing energies measured in E' K plus and the proton binding energy obtained from E'' cross-section. So the E'' will provide baseline to extract information in a model-independent way. So this use of LED appears to be uniquely suited to study this medium. Okay, and the JLab at the moment is the only laboratory where you can make this experiment. Okay, these are the data from Hadong probe. As you see, that's very good, very nice. Okay, effects, shell effects. But as you increase the A, you see that this degrades. And okay, so if you look at the very nice review by Hashimoto and Tamura, they said that this is the best proof ever of quasi-particle motion in a strongly interacting system. It is impressive. Anyway, but okay, in the LED you see that the levels are barely seen. You can do much better with electron probe also, because you can really calibrate well, and you have more precise lambda single particle energy determination. Okay, so it's vital and so it's okay. It's important to do these experiments. Okay, spectroscopy. We know that there are plants at Keck to provide to produce high resolution beam. We saw from the talk of Nakamura this morning the exceptional missing mass resolution expected, and this is very good because they are complementary probe, the complementary approach. So okay, so these are the two. These are the simulation and theoretical calculation done by Millener and Motoba. Of course, you are not interested in detail for the result detail of what is behind this. You are interested in what happens in the main peaks, S lambda, P lambda, etc. You see that are easily distinguishable with the resolution we can have. And this is, okay, as you see, that's also, you can separate without any problems. Subtract background, you should not have a problem. Even with 800 kV resolution, this is what we expect to get for this very high mass nucleus at Jefferson Lab. Okay, this is the experimental apparatus. Initially, we have done this. We proposed to have the best from Olay, and we have done these experiments in Olay and in Olsey. We decided to have the best from the two holes, and so we had to do in Olay. This was the best in principle, using HRS for the electrons and HKS, which is much higher angular acceptance, so much higher counting rates possibility. And but okay, for practical reason, we are obliged to go in Olsey that we have slightly different kinematics. So this I see here preliminary, because what we used is the cross-section given to us by Professor Moto, but this has to be evaluated because the kinematic is slight difference. Essentially, the angular of virtual photon with the kaon is slightly different. But as you see, we have except a very good signal to noise ratio, so you shouldn't have a problem in detecting also the very small, also small S shell peak. So there are some challenges in principle in these experiments. One is the target. Everybody used the LED target knows that this is a delicate one for it. But we have used it at Nigef with the 10 micron pierce instead of the 25, but that we will use at Jefferson Lab. But we will have cryocooling instead of water cooling, so we have not problem, because it's been shown also by covering with the simulation and also measurements with the laser, so we have no problem with this. So it's not will come the same. By ID also, you know, sometimes it's like find the needle in an haystack, find the huge background of pion and proton, especially pions, very close in mass to this. But okay, the very good HKS detector that is has this excellent pion rejection capability will allow us to do the experiments. But in any case, we have used in the previous experiments our rich detector that has even been upgraded for another experiment, so we could have 10 to the 10 as a pion rejection factor. So we have no problem. Let me conclude. So, okay, it's quite obvious, it's just resuming what I've said until now. Let's say that this measurement, along with those on lighter nuclei, will provide valuable information on YN and YNN interaction. These experiments are well positioned in theoretical and experimental in the framework of the pernuclear collaboration proposal that are calcium-40, calcium-48. Also, what has already been described, but the experiments were already described, the result by Li Wang-Tang, determining unknown lambda n interaction by investigating lambda n resonance. So all of them, all these experiments will give a contribution on the best knowledge of the lambda n and lambda n interaction and their impact on astrophysics. Thank you.
Thank you for your talk, Franco. Other questions or comments or?
It's lunchtime, so yeah.
We are late, so maybe we should.
Can I ask?
Please. Sorry.
Oh, thank you very much. It was interesting to find that from the E prime P, then you determine the proton energy inside the lead nucleus and use it as the calibration or some other part of the interaction, calculation of the spectrum. And if that's true, then it is also possible to calculate the E prime K plus and E prime K plus on calcium-40 and calcium-48 targets, where the Ronaldoni predicts that there may be some energy difference from the single particle spectrum of the lambda. Do you have any plan to do such kind of calculation as well as E prime P experiment on calcium-40 and calcium-48?
E prime P on calcium-8 and calcium-48 has been done by us in Saclay in the 80s. So we have results for calcium-40 and calcium-48. We did this experiment in Saclay in the late 80s. So we have this results if needed.
Then you have all the result preparation.
We have this data.
Okay,
By
then
chance, because we had done these experiments. I've worked in Saclay in the 80s. In different experiments, starting from carbon, we did the first separation E prime P cross-section separation on calcium-40, calcium-48. So we have this data.
Thank you very much.
Okay. Other questions? If not, let us thanks again. Now the session is over.
interesting, and some people think that we started 1:30 and we are starting 15.
I'm very, very sorry.
No, okay. So go ahead.
Okay,
It's your call.
Let's start the afternoon session. I'm very sorry to be late. And the first speaker is Makoto Oka, and he will talk about chiral effects.
I cannot hear you.
Application to heavy and spectrum. Okay, and you have
microphone.
Oh, hello? Oh,
Yes.
okay. You have a 13-minute talk and 2 minutes discussion. Okay, please start.
Okay, thank you, Onishi-san. And I'd like to share screen.
We can see your slide.
Okay. Thank you very much. I'd like to thank the organizers for giving me a chance to give a talk, although I cannot attend the conference in person. My talk is on the chiral effective theory of dike-quarks and application. This is my contents. And let me start with the introduction of dike-quark. As you know, the dike-quark is the simplest colorful clusters in hadrons, and either class 3 bar or 6, so spin 0 or 1. But among them, S-wave class 3 bar dike-quarks, spin 0, scalar dike-quark, and spin 1, axial vector dike-quarks are strongly correlated. And actually, the spin-dependent forces like magnetic gluon exchange predicts a strong attraction in the scalar dike-quark, typically a 200 MeV between the scalar and axial vector dike-quarks. There's some lattice calculations, and from old days to new one, and the most new one done by the Chinese people give a full QCD calculation of scalar and axial vector dike-quarks and others, and they have some mass differences of dike-quarks of this order. In hadron spectroscopy, the dike-quarks can be seen in the heavy baryons most effectively. For instance, because of the heavy quark spin symmetry, the spin of the dike-quarks can be separated from the spin of the heavy quark, and so the dike-quark spin can be extracted easily. And in the charm of bottom sectors, the lambda C, lambda B, and the sigma C's and sigma B's are split by 200 MeV or so because of this dike-quark correlations. That can be even seen in the strain sector, and in fact, in the quark model calculation, the probability of so-called lambda mode excitation and rho mode excitations in the P-wave excited baryons can show even in the strain sector, lambda mode is quite dominant. So in the strain sector, also we can see the dike-quarks. Dike-quarks may appear in the exotic hadrons and hadronic matter, like doubly heavy tetraquark systems or the Bose-Einstein condensates in this hadronic matter. So the purpose of this study is to explore the properties of light dike-quarks under the SU3 cross SU3 chiral symmetry, and see what are the chiral partners of dike-quarks and their implications in hadron spectroscopy. How do we observe the chiral properties of dike-quarks? How do dike-quarks behave in matter, especially when the chiral symmetry is partially restored? I should mention that there are some previous works on the chiral effective theory of dike-quarks from various different points of view. Donkey Hon's group and Hatsuda-san and Kawakami-san's group have done some work. In recent couple of years, we have published several papers on this subject, formulating the chiral effective Lagrangians and its applications to heavy baryon spectrum and decay widths and also doubly heavy tetraquarks. I will show some of the results. Okay, let me use a linear representation of chiral SU3 cross SU3 for right quark and left quark, and scalar chiral diquarks can be formed by right-right or left-left combinations in color 3 bar, chiral 3 bar 1 and 1 3 bar. And these can be combined into parity eigenstates into the scalar diquark and pseudoscalar diquark in this form. They belong to 3 bar 1 plus 1 3 bar representations of chiral symmetry. Using this diquark definition, we can construct the chiral effective theory of diquarks in terms of the linear sigma model approach. And up to second order in sigma field, sigma is a meson field, we can write down the chiral Lagrangian like that. And we see that there are 3 terms which are relevant to the masses of diquarks when the chiral symmetry is spontaneously broken. The first term, M0 square, is chiral invariant mass term, while the second and third terms are contain sigmas, so that only when the spontaneous symmetry breaking of chiral symmetry, the mass will be generated. Furthermore, this second term is very interesting, which is which also breaks the actual U1 symmetry. So this is U1A anomalous term. By using these 3 mass terms, we can write down the masses of the right and left diquarks and under the spontaneous symmetry breaking in this form. This is right-right component, left-left component, and left-right, and so forth. Now, by diagonalizing this, we get the scalar positive parity and negative parity diquarks, and their masses are split by these M1 square and M2 square terms according to the chiral symmetry breaking. I can just mention that the second term, M1 square term, is anomalous in UA1. That can be seen from this diagram that it has 3 left quarks and 3 right quarks. 3 right quarks are getting into this vertex and 3 left quarks are going out. So this induces the flavor UA1 breaking. On the other hand, M2 square is UA1 non-anomalous. Actually, because of this UA1 anomalous term, we see a very interesting phenomenon when the SU3 is explicitly broken due to the strange quark mass. And then we found that there is an inverse mass hierarchy. That is for the scalar diquarks, UD diquarks are lighter than SU diquark. But for the pseudoscalar diquark, UD is higher than SU, so that the mass orders are inversed. Okay, now using the single using the diquark heavy quark potential model, we calculate the heavy baryon mass and doubly heavy tetraquark mass using these informations from diquark because diquarks are not directly observed. So we use a simple potential model between the heavy quark and diquark, or 2 heavy quarks and anti-diquark. The parameters are fixed by various previous information. And here's a typical mass spectrum of baryons with scalar and actual vector scalar diquarks, and scalar and pseudoscalar diquarks. And here's a lambda C ground state and CC ground state. But in the low mode, where the diquarks are excited, this mass inverse hierarchy of mass will appear in this spectrum. We also introduce actual vector and vector diquarks similarly, but in this case, there is no UA1 anomalous term, and we have several mass terms also again. And by diagonalizing this, we get masses of actual vector and vector diquarks in this way. We have a Gelman-Oakwood type mass formula in this case. Now, this is a full spectrum of single heavy baryon, charm baryons, and one sees that sigma C is in the C prime. This is a flavor 6-state C, and omega look very similar, while this lambda C and CC of 3 bar are very much different. And so this is one of the results of chiral theory. Now, another interesting thing is the mass crossing we found for the between 0+ and 1+ diquarks. When the chiral symmetry restoration occurs, then the value of chiral condensate changes from 1 to, say, 0. 1 is F pi. And then in the middle, the scalar diquark mass going up while the axial vector diquark goes down, and therefore there may be a crossing occurs. And this must be very significant when we consider the heavy baryon masses in the dense matter. Okay. This is the spectrum of doubly heavy tetraquarks we calculated using this diquark model. And we find bound state in BB U-bar-D-bar system, while there is no bound state in CC U-bar-D-bar in our model. There's also excitation of a QQ bond, which comes lower compared to the excitation of the diquarks. Okay, here's a comparison of various calculations of WB U-bar-D-bar and WC U-bar-D-bar, and they are almost consistent. Some of them are lattice QCD, and some of them are Quark model calculations. And they consistently give a bound state in the BB U-bar-D-bar system. Okay, this is my conclusion. So we formulated the chiral effective series of scalar and pseudoscalar diquarks and axial vector and vector diquarks. Actually, U1 anomaly seems to be very interesting to give this inverse mass hierarchy in pseudoscalar diquark spectrum, namely UD pseudoscalar diquark is heavier than the SU diquark. Spectrum single heavy baryon is calculated, and the inverse mass hierarchy appears in the low mode excited states, and make lambda Q and cascade Q spectra very much different. Under chiral restoration, we find that mass crossing occurs between the scalar and axial vector diquarks, which should give significant effects in the behaviors of heavy baryons in dense matter. Applying double heavy tetraquarks, we find the bound TBB state. Okay, that's all. Thank you very much.
Thank you very much. Thank you very much for a very interesting talk. Okay, this talk is open for questions and comments. Hirohio?
The slide before that, I mean, you have results for the TCC.
Yeah.
Yeah, that one, I mean, TCC and their predictions there. You know, I mean, the TCC, okay, that we know there. And no, it's okay, yeah.
TCC, right?
I
yeah.
mean,
yeah.
But
just
you
that,
see, I mean, the thing is that these states are bound by 200, 300 MeV, no? I mean, and then I see the discrepancies. Yes, the TCC.
This is not bound.
TCC.
This is not bound.
No, this is not bound.
This is not bound.
Yeah.
Well, but you remember that this is the diquark model, so that U-bar and D-bar can never be separated. Yes. So this is completely different from a molecular type model. Okay, but so this cannot reproduce any threshold type resonances.
Right. So I mean, could you accept that? I mean that this is something in favor of of the molecular picture for the TCC.
The TCC at the threshold must be must contain a lot of molecular components. Yes, I agree with that.
Okay.
But the TBB is different. This is deeply bound somehow.
TBB, I mean, I will.
We believe that this is a compact state.
I'll show in my talk. I'll show in my talk. I also get a mean TBB
okay.
bound states.
I will wait. Wait for 1 hour. Okay.
One short question. Okay, would you please tell me the relation between your your model, Dai-Quok model, and the mirror assignment for baryons and their other hadrons?
That's an interesting question, but as I mentioned, that the UA1 symmetry anomaly gives some interesting feature on this mass hierarchy. And this, I believe that because UA1 anomaly can mix the QQ state with the tetra Dai-Quok, namely QQ bar state. Okay, so this inversion is related. It seems to be related to that. So that is also related to mirror kind of assignment in the Dai-Quok system. Yeah.
Thank you very much. Other question? Okay. Okay, let's thank the speaker again.
Thank you very much.
Okay, next speaker is Miss Tomona Kinugawa from Tokyo Metropolitan. Are you here?
Yes, I'm here.
Okay, would you please share your screen?
Okay.
Okay, I can see, but please make it full screen. Okay, we can hear and we can see. Okay, please start.
Okay, thank you for the introduction. I'm Tomona Kinugawa from Tokyo Metropolitan University. And first of all, let me thank the organizers for giving me an opportunity to give a talk in this conference. Today, I'd like to talk about the structure of the exotic hadrons by the weak binding relation with the finite range collection. My collaborator is Hyodo-san, and this study is summarized in this paper. Okay. So in recent experiments, many candidates for exotic hadrons have been discovered, and those are considered as, for instance, the hadronic molecule states with a weakly bound state of hadrons. And here, we'd like to analyze the internal structure of the candidates for exotic hadrons with model-independent manners from observables. For this purpose, we consider the compositeness and the weak binding relation. We expand the hadron wave function into the hadronic molecule states and the others. Then we call the weight of the hadronic molecule compositeness. Then we can derive the weak binding relation in this way, where A0 is the scattering length, R typical is the interaction range, and R is the radius determined by the binding energy. When the binding energy is very small and the correction terms are negligible, we can determine the compositeness only from observables. And therefore, we can determine the compositeness without any specific models with this weak binding relation. And we can analyze the internal structure of shallow bound states with this relation, whether the hadronic molecule states or not. Now we consider the weak binding relation from the low energy universality. From the consequence of the low energy universality, the radius equals to the scattering length. And the terms of X compositeness and R typical is considered as the origins of the deviation from the low energy universality is equals to R. And now we consider another origin of the deviation as the range correction by introducing the effective range to the weak binding relation. To the study of the range correction, we consider single channel and zero range model. In the single channel case, there is only a hadronic molecule state, and therefore the compositeness equals to unity by the definition. And in the zero range limit, where the interaction range is completely zero, the correction terms are also 0. And therefore, it seems that the weak binding relation reproduces the consequence of the low energy universality is 0 equals to R when we apply the weak binding relation to this model. However, when we consider the renormalized scattering amplitude, we find that deviation from A0 equals to R because of the effective range, and we find the range correction in the weak binding relation from the effective range is appeared in this way. So from the discussion above, we propose the improvement of the weak binding relation by redefining the R typical in the correction terms. In the previous weak binding relation, the interaction range is denoted as R typical, but now we denote it as R interaction. And then we redefine R typical as the maximum length scale among the interaction range and the length scale in the effective range expansion, R effective. For example, R effective is a magnitude of the effective range, normalized shape parameter, and so on. And we note that this redefinition of R typical reduces the previous weak binding relation for the R typical equals to the interaction range. Then we perform the numerical calculation to study the applicable region of the weak binding relations. For the numerical calculations, we use the effective range model, which has two length scales, the effective range and the interaction range. And then we determine that the weak binding relation works when the validity condition is satisfied. This condition means that the exact value of the compositeness is contained in the estimated region by the weak binding relation. And then we show the applicable region of the previous and improved weak binding relations in R-int and RE plane. In the region 1, we find that both previous and improved weak binding relations are applicable because the validity condition of both relations are satisfied. However, in hatched region 2, we find that only improved weak binding relation is applicable because a validity condition for previous weak binding relation is not satisfied. So therefore, the range correction enlarges the applicable region, region 1 to region 1 plus 2. Then we apply the improved weak binding relation to the actual hadron and hypernuclei and atomic systems. As an example of the typical hadrons, we consider deuteron. And we consider X32 and D-surface as an example of the candidates for exotic hadrons. And N omega and omega omega divaryon are considered as an example of the states obtained by the lattice QCD calculations. And we also consider a hypertriton as a nuclei system, and helium-4 dimer, which is a weakly bound state of the helium-4 atoms, is considered as an example of the atomic systems. And we can see that the low energy universality holds because the scattering length is much larger than the interaction range for all states, and we can use same weak binding relation for those bound states despite the difference of the interaction. And we can also find that the bound states other than D-surface and hypertriton have larger magnitude of the effective range than the interaction range. And it is expected that the range correction is important for those states because redefining R typical equals to the magnitude of the effective range for those states. And we note that the interaction range is not unobservable, and we determine our interaction from the theoretical considerations. And then before the estimation of the compositeness, we show those band state plotted in the applicable region of the effective range model. And then we find that X72 is in the applicable region only for the improved weak binding relation in region 2. And then we need to use a improved weak binding relation for the reasonable estimation for X72. And we note that this applicable region is model dependent, and herein for dimer, and N omega divalyon is close to the applicable region of the previous weak binding relation, region 1. And in fact, for N omega divalyon, when we consider the lower bands of the compositeness, the lower boundaries of the compositeness of N omega divalyon is larger than 1 unity, and this is it is contradict to the definition domain of the compositeness. And we find that for N omega divalyon, we also need to use improved weak binding relation for the reasonable estimation. So in summary, the range correction is important for X72 and N omega divalyon we find. And finally, we estimate the compositeness from the weak binding relation with the uncertainty band defined in this way. The definition of the uncertainty band restricts the estimated compositeness within the definition domain of the compositeness, 0 to 1. In this situation, the upper bounds of the uncertainty band is unity. And we show the estimated compositeness with the uncertainty band in this table. And we find that those bound state, all of bound state are composite dominant because the compositeness is larger than 0.5, which is a boundary of the composite dominance or not. And we also compare our result for X1372 with model calculations of Takizawa-san and Takeuchi-san, and we obtain the compositeness with this domain from their model calculations. And we find that for X1372, model independent calculation is consistent with the model calculations. So in summary, the weak binding relation is useful to determine the internal structure of the shallow bound states. And we study the range correction to the weak binding relation and propose the redefinition of the R typical in the correction terms. And then we find that the range correction enlarges the applicable region of the weak binding relation. And we apply the weak binding relation to the actual Hadong system and find that the range correction is important for the reasonable estimation of the compositeness. That's all. Thank you very much.
Thank you very much for clear talk. Okay, the question, comment, and you're here.
Page 8 and 9. Page 8. I mean, are these your predictions for X? I mean 168, plus, minus, whatever. I mean, for the Neutron, I mean, all numbers there are everything should be smaller than 1, and practically all your results are bigger than 1. That is not, I don't consider that a very successful prediction. particularly when you have, the errors, so big. So, then I want to call your attention. You probably know the work, recent work, the Lianrong Dai and Jing Song and myself, in which we do something similar, also taking into account the range of the interaction. But the method is very, it's just pure luck. We were lucky. But the method is very good because starting from A and R0, we predict with much better precision than that and with results smaller than 1. We predict, the compositeness. And at the same time, the thing is so good, it gives you the range of the interaction for free. You don't have to make any assumption. The same method tells you which is the range of the interaction. So, we were lucky. I don't say anything. We were lucky, but the method works very well. It's very good. Look at it. It is very, very, very good.
Yes. Okay. Okay. I read your paper, and we think that our estimation is also reasonable because of the definition of this uncertainty band. So we think.
But I wanted to ask, in fact, what is the difference between, what is the difference between this table and the table in the page before? What did you do, to pass from there to the other?
To
pass from this table to the other table, what did you do?
A difference of this table and this table.
Yes.
This table is just a result from the weak binding relation. So this is just a result from the weak binding relation, and this is a results with the uncertainty band. We do not consider the estimated compositeness, estimated range of the compositeness.
Difference of max and int. Is it correct?
Yeah.
Maybe? Yeah. Maybe I'm sorry.
Okay, I see. Well, I see.
Okay.
I'm
sorry, but I have to, time is up and we have to cut. Okay, let's thank the speaker again.
Thank you very much.
And the next speaker is also from online, and Chandra Sekal, Akron Akondi. And okay, are you here? Would you please share the screen? Share your screen.
Yeah.
And share your slide. We do not see.
Just give me a second. I'm trying to share.
Okay, I can see, but make it full screen.
Yeah, wait. Can you see it now?
Okay, we can hear you, we can see you. Okay, he will talk about Xi-star production from GlueX. Okay, please start.
Hello, good morning all. I'm Chandrasekhar Akpandi. I'm doing a postdoc at Florida State University, Tallahassee, Florida. Today, I'm presenting the results of Excited Cascade 1820 on behalf of GlueX collaboration. And thanks for giving this opportunity to share our results with the world via this Hyperon conference platform. Oops, sorry. Yeah, this is the outline of my talk. Just I will go with what is the motivation to do the research, what are the previous experiments, and what is GlueX experiment, sorry, and event selection and the results from the GlueX photo production cross-section of the cascades and the summary and the future work. Yes, the motivation section is actually, it's a quite straightforward one. We all know decouplets and octets and decouplets. SU6 flavor symmetry gives us 20 antisymmetric, 70 mixed symmetric, and 56 symmetric states. And this 70 mixed antisymmetric symmetric states can be decomposed into one decouplet, 2 octets, and 1 singlet state. And when we combine this with the one orbital momentum of L equals to 1, that's a negative parity 1, gives us octets. Combination of spin with 3 by 2 gives us 3 half, 1 half, 5 half, with negative parity, and octet with 1/2 with L equals to 1 gives us 1/2, 3/2 with negative parity, and decuplet with S equals to 1/2 gives L equals to, combines with L equals to 1 gives 3/2 and 1/2. This is quite straightforward textbook one. And on the right hand side, we all know the decuplets and octets, and the cascades have been highlighted with the blue. And with the excited baryon spectra from lattice QCD, where can we see this? All these seven states actually predicted with lattice QCD. And these are the 7 states. Decuplet ones are shown with yellow in color. 5 octet ones are shown in blue color. These 7 states actually are accessible at GluX energies. In other terms, they are below 2.1 GeV of energy. So we can see them at a GluX energies. And the motivation section is continuing. Actually, how can we see these excited cascades? Basically, we see the excited cascade by their decay modes. And the decay modes, this excited cascade can be seen as 2 strange quarks or heavy quarks, and one either D quark or U quark as a lighter quark. In the left-hand side, the excitation between 2 heavier quarks is a rho mode, and the excitation between the composite system of 2 heavier quarks and the lighter quark is lambda mode. The Capstick and Insger, or Tao Chow and Insger, they made their predictions and their calculations on these excitation modes. And based on that, the decays of the rho mode is predominant K, Y, hyperon. And lambda mode is cascade and pi. So based on this decay modes, we can see, okay, what is the excitation between which quarks are excited and which is giving us this excited state. So if we see the cascade excited spectrum and add L equals to 1 to the ground states, we already knew there are 7 excited states according to QCD, but these mass 1620, 1660, 1690, 1820, 2030, 1950 are the only excited states with the 2 stars and 3 stars and 4 stars, 3 stars. So if we give this 1/2, 3/2, 5/2 minus, these are the lowest excited states within the rho mode. They are really narrow width. And 1620, is it a 1/2 minus or 3/2 minus? We don't know. It may be a radial excitation. If it is a radial excitation, then it should be like 1/2 plus, not 1/2 minus. And even 1950, we don't know whether it is 1/2 minus or 3/2 minus. But interestingly, in the previous experiments with K minus lambda, invariant mass spectra in the CERN late 70s, clearly there is a 1820 peak is evident in the K minus lambda mass. And a missing mass square in the same BNL experiments using K minus proton reaction with the missing mass of K plus, 1820 is evident, 2030 is evident, 2022, 2370, but there is no indication of 1620 and 1690 states in both of these. Interestingly, the latest Bellet result shows 1620 is quite evident and 1690 is a kind of evident but suppressed. And 1620 is a very broad peak. And what can we say? This very broad peak is either it's kind of like 2 states sitting on top of each other. That is one of the kind of like really interesting question. And 1690, if you see it, it is suppressed in cascade pi. So it can either be K lambda. And that is actually the interesting things we found out from our previous experiments and the theoretical studies. So we thought, okay, maybe it is really interesting to work on cascade excited cascades. So this is we are doing it GluX. GluX experiment is located in Hall D, Jefferson Lab. This is the aerial view of Jefferson Lab. A, B, C are the halls. This is the Hall D. GlueX started data taking in 2017, and the right-hand side figure is hermetic acceptance charge and neutral particles of GlueX apparatus. Different electron beam incident on the radiator produces Bremsstrahlung photon incident on the target. In this case, it's a liquid hydrogen target. We have star counter, dielectric calorimeter, time of flight, forward calorimeter, forward drift chambers, and lift chamber solenoid. Actually, one of my colleague, Peter Pauli, is giving a complete strangeness programmatic GlueX as a plenary talk in this Hyperon conference. So please do attend for more information about GlueX and what we are doing in details. Yes. Now comes to the excited cascades studies. We have selected the events for the reaction gamma P goes to K plus excited cascade minus decays into K minus lambda decays to pi minus proton. If you see this reaction, it is a combination of all the three: electromagnetic, strong decay, and weak decay. That's the most interesting thing with this reaction. And we selected the events, all the events which are kinematically fitted. And GlueX phase 1 data has been used in this, which is 2017 January, 2018 January, and 2018 August. And we have 2019 the data is there, but still we are processing that data. So that's the phase 2 data. We are going to include that in our further analysis. We selected events after relevant cuts, such as chi-square cut, and obviously K plus K minus is there. So phi background is there. We neglected the events with phi background, lambda invariant mass cut, and lambda path length cut, and all the list of the cuts have been given in the backup slides. And we used Monte Carlo simulation generated with single hyperon of mass Y0 star of 2.75 GeV with width of 0.5 GeV. And we used a T-slope value of 1.4 GeV square is used. And when we reconstructed the K minus lambda invariant mass for a particular energy bin of 7.7 GeV, clearly we are seeing 1820 peak, but 6090, 1950, 2030, 2120 peaks are supposed to be there, but we did not see any of those. That's kind of like a really interesting one. Our main aim is like, okay, we want to see this 60 and 90, 1820, 1950, 2030, because they all have K minus lambda as 3-star or 2-star decay. So we expected that. Previously, with the K-on beam, they have seen it. But with the photo production, somehow 1820 is the dominant peak, and rest of the peaks, excited cascades are not evident, which is kind of really interesting. And we don't know. We are trying to figure it out. Then we divided the entire K minus invariant mass for different energy bins. This is with the 6 energy bins from 6.5 to 11.6, 11.4 GeV. And invariant mass has been fitted with a combination of ocean and Argus function for the background and ocean for the signal. And once we have this real data yields, it's quite easy. And we used Monte Carlo simulation with the Y0 star of 2.75 GeV and 0.5 GeV of width with the T value 1.4 GeV square. We calculated the efficiency with this is the luminosity number, which is really good. And efficiency, we have calculated the efficiency, and this is the efficiency plot, which is kind of, we can say, very low in efficiency because of photo production. And one thing is like we are generating 2 strange quarks out of 0 strange quarks, like photon incident on the proton, so 0 strangeness, suddenly it has to appear as 2 strange quarks. So efficiency can be little low, as we can expect that. And then once we have this efficiency, real data yields, it is quite straightforward to calculate the total cross-section. But unfortunately, here we don't know the branching ratio of excited cascade is decaying into K minus lambda. So what we did is total cross-section times the branching ratio, and we calculate with the quite straightforward formula, yield over target times flux times efficiency. These are the preliminary results of total cross-section times the branching ratio in nanobars. And one of our Hardy class collaborators estimated the upper limit for the total cross-section for excited cascade 1820 is 1.01 nanobards, but it's of the different energy range, 1.6 to 3.85 GeV. So that is in the lower energy level, lower energy being, so it's a kind of like a smooth fall off. So these results are within that range measured by the JT quotas and etc. all. And in summary, in K minus invariant mass plot, excited cascade 1820 is the only dominant signal. Excitation is probably likely between the pair of strange quarks, as we have seen with the pictures, predictions given by Simon and Tao Chow and Itzger, with lambda decay, rho mode decays to K minus lambda. So it's the excitation likely between the pair of strange quarks. And total cross section is below the upper limit estimated by class. Class data is mostly in the range of 1.6 to 3.85 GeV. So it has been like smoothly decaying. And future work, we would like to measure the differential cross section for the different deviants. And a spin-off excited cascade 1820 is one of our immediate interesting thing we would like to measure. And we want to include GlueX phase 2 data, which has more statistics. So GlueX acknowledges the support of several funding agencies and computing facilities. Thank you all.
Thank you very much. Very nice talk with interesting data. Okay, this talk is open for questions and comments. Okay, I have one question about the nature of the exile star, speciality of 1820. Is it because of the final state pair of K minus lambda or the photo production, which is the specific characteristic feature of 1820?
That is kind of really interesting one. To be honest, I don't know the answer because it can be like photo production is maybe the speciality of the photo production, which is actually producing 1820, or maybe it's a decay of cascade K minus lambda. Actually, that's kind of interesting one. That is one of the reasons we want to see more excited, like 1950 or 2030. If we have seen it in GlueX phase 2 data, at least we can say it is with the K minus lambda. If we did not see that, those rest of the excited cascades, we don't know. Maybe this is one of the specialties of 1820. That's what I can say. Because just out of the blue, we have to produce two strange quarks from zero strangeness in photo production. So
it seems that more theoretical work is necessary to clarify this resonance. Okay.
Sorry?
Okay. Yes. More theoretical work will be necessary to understand this one. Okay.
Yes, so, okay. To be honest, like I don't have a specific correct bullet point answer to your question, actually.
Short.
I'm sorry, I don't have here the paper, but I vaguely recall that the 1820 is one of the states that Saurabh Sarkar, you might know him, you are also Indian, got from the interaction of pseudoscalars with the decuplet of the baryons. For example, K minus sigma 1385. That would be the main channel bound by about 40 MeV or something like that. You can have a look at that paper. Sarkar, Vicente Vaca, Sarkar. And
yes.
Because I vaguely recall, I don't have the number, but I vaguely recall that this was one of the states that we got.
Let me see. Sigma.
Okay.
And K sigma, that's what you're talking about, right?
K bar sigma star 1385. K bar sigma star 1885.
K sigma, right?
K bar sigma star 1885. Decuplet, the sigma of the decuplet.
Okay.
Yeah, definitely. I will take a look at it then.
Please check the reference. Okay. Okay, let me stop here and thank you very much. Thank you again for the speaker. Next speaker is Indico. We follow Indico program. In the Indico program, Takuma Nishibuchi is earlier. I'm sorry. And the next speaker is Takuma Nishibuchi, connecting from online. Okay. Would you please share your slide?
Can you hear me?
Yes. Would you,
Okay, thank
would you
you.
speak again? Is it howling or not? I'm not sure.
Can you hear me?
Yes. Okay. Please start. He will also talk about the Guzai star. Please start.
Thank you for the introduction. I'm Takuma Nishibuchi from Tokyo Metropolitan University, and my collaborator is Hyodo-san. Today, I'd like to talk about nature of excited Guzai baryons at Renaissance. So, first, we talk the motivation of this study. Guzai 1620 and Guzai 1690 are the excited state of the baryon Guzai with strangeness -2. While various theoretical studies have been performed for the excited Guzai 1620 and Guzai 1690 states, their nature was not well understood due to the lack of experimental data. Recently, as shown in figure, the invariant mass distribution of pi Guzai in the Guzai C to pi pi Guzai decay was observed by the Bell collaboration. Both Guzai 1620 and Guzai 1690 are seen as peaks in invariant mass distribution. But the peaks of Guzai 1620 and that of Guzai 1690 are so close to the threshold of k bar lambda and k bar sigma respectively. In the analysis by Bell, this invariant mass spectrum is fitted by the simple bright signal distribution without the threshold effect. But in general, it is known that the near threshold peak is affected by the thresholds. Then our aim of talk is as follows. First, we construct the model of Guzai 1620, which reproduce the Bell data. So we then study the threshold effect on behavior of the peak of Guzai 1620. Next, we show the formulation of the scattering model. The coupled channel meson baryon scattering amplitude, it represents as T, and it satisfies this scattering equation. W is the total energy of the system. Indices I, J, K represents the meson baryon channels, for example, pi Guzai, k bar lambda, and so on. V and G correspond to the interaction kernel and loop function, respectively. Substituting T iteratively, we find that the T contents term up to the infinite order. We show the Feynman diagram which corresponds to expansion. The diagram may be interpreted the meson baryon multiple scattering. The scattering amplitude T can be represented by V and G by solving the above scattering equation. Here we show details of V and G functions. V is the interaction kernel, and we use the Weinberg-Tomoza interaction in this study. It is a S-wave interaction satisfying chiral low energy theorem. Fy is the meson decay constant, and Mi is baryon mass. Cij is group theoretical factor, and it expresses strength of interaction. For example, negative C represents an attractive interaction, and the positive C represents a repulsive interaction. Ni is kinematical coefficient from spinor, and is reduced to unity at the thresholds. G is the loop function, where the divergence is renormalized by dimensional regularization. Then GG becomes the function of W and AI. AI is the subtraction constant of the channel I, which plays a role of the cutoff in each channel. Next, we show the scattering amplitude of previous study. The previous work studied Decay 1620 in same formulation before the Bell experiments. The mass and width predicted to be 1607 MeV and the width 280 MeV, respectively. To compare Decay 1620 in the previous study with the Bell data, we calculate the scattering amplitude F of the scattering F of pi Decay. The result is shown in this figure. Horizontal axis is the total energy W, and vertical axis is scattering amplitude F. The scattering amplitude F is complex, so F has real parts and imaginary parts. The real part is shown by the straight line, and the imaginary part by the broken line. In this figure, there is no distinct peak of imaginary part of the scattering amplitude due to the broad decay width. Let us improve the model to reproduce Bell experiments. The strategy is as follows. The Bell experiment reported the distinct peak with a narrow decay width. Mass and width 1610 MeV and 60 MeV. At first, we assume that the pole is located at 1610 minus 30 I MeV, which is defined as d Bell. Next, we call the pole in the theoretical model ZTH, and we define delta Z as the distance between Z and d Bell and ZTH. To improve the model, we adjust the subtraction constants in the pi Decay and k bar lambda channel, which located close to the Decay 1620 peak. We stand for the subtraction constants. We search for the subtraction constants which minimize delta Z. We then show the result of minimization. In the figure, we show the density plot of delta Z with respect to the subtraction constant in the pi Decay and k bar lambda channel. Horizontal axis, the subtraction constant of pi Decay channel, and vertical axis is the subtraction constant of k bar lambda channel. The delta Z is larger. The delta Z is larger where the color of density plot is closer to yellow, and the delta Z is smaller where the color is closer to dark purple. Now we research the subtraction constant, which minimization the delta Z, so the desirable value at the point where the color is close to dark purple. In the previous study, subtraction constant of both a pi Decay and ak bar lambda are set as -2. We find that the delta Z is 0.1 MeV that achieve that a pi Decay is -4.19 and ak bar lambda is -0.14. Then let us compare the scattering amplitude in this study with that of previous study. The figure shows the real and imaginary part of the scattering amplitude of here shows the real and imaginary part of the scattering amplitude of this study by the thick orange lines and those of previous study by thin purple lines. Horizontal axis is the total energy W, and vertical axis is scattering amplitude F. The straight line represents the real parts, and the dashed and broken line shows stands for the imaginary parts. In the previous study, the imaginary parts shows no distinct peak due to the broad decay width. On the other hand, in this study, a distinct peak appears in the imaginary parts because of the narrow width. There is a distinct peak on real axis like Bell results. Next, we compare the scattering amplitude, which is obtained in this study with bright trigonal distribution, which has same peak as Bell experiments. Horizontal axis is total energy W and vertical axis is scattering amplitude F. It is same as previous slides. The figure shows the real and imaginary part of the scattering amplitudes of this study by thick orange lines and the bright regional distribution, which has a pole at the same position as the result of this study by thin green lines. So the existence of a threshold effect can be clearly seen by comparing the imaginary part of both amplitudes. Namely, the peak position is shifted and the shape is distorted by the threshold effect. Finally, we show the summary of this talk. First, we construct the coupled channel scattering amplitudes with Guzai 1620 peak as reported by Bell collaboration. Next, in comparison with the bright regional distribution, we found that the near threshold resonance peak is distorted by the threshold effect. So caution must be paid to determine the resonance pole near the threshold. Then in our future plan, we would like to study Guzai 1690, which was not tested in this study, and to perform numerical calculation of Guzai C to pi Guzai decay. That's all. Thank you for listening.
Thank you very much. Thank you very much for. Thank you very much for your nice, clear talk. And this talk is open for questions and comments. Okay, you.
Hi, thank you for the talk. Just as far as I understood, as only ingredient or as only diagram you are using in the kernel is Wimber-Tomozawa, right?
Yes, Wimber-Tomozawa we use.
Okay, so then, yeah, if you look to the old works, I'm talking about the work you were mentioning as the pioneering, this Ramos and Osset and Benhol, and also there is another one from Sekihara. They are using the same kind of interaction kernel, and they get rather big, as you showed, imaginary part for the pole. So I am a little bit surprised that you, without including any modification in the imaginary part, because the only contribution you could get is from the loop function, you have reduced considerably your imaginary part, your width. So do you have an explanation for this?
Explanation.
The previous.
Sorry, please.
So when you are showing the poles you found, yeah? Here.
Here.
No.
Previous to previous. Yes. No.
No, one more.
One more. Page 6.
Page 6. Okay.
Okay. You see the imaginary location of your pole, yeah, or both. So particularly, I'm focusing the first one. Yeah. In this, you found that 1,610, and the imaginary part is 30. So yeah, I'm curious.
So in this work, we found only this pole. So another pole is not appeared in this work.
No, don't. It's okay. Don't worry. It's okay.
Okay. Please go to look at the Sekihara paper somewhere. Okay.
Okay.
Okay. Let me stop here. Okay.
Thank you.
Thanks, the speaker again.
Thank you.
Sorry for you to wait. You're here. It's next. Yes, next one. It's you. And for online speakers, please refer to the slide uploaded on the web. Okay, then Zoom will show
The last
the
talk
slide.
will be in person, so first one. And I'll talk about, exotic states, meson exotic states, those that cannot have a QQ bar structure. And since we have a meeting on kaons, right, and hypernuclei, I will make connections of kaons. So I will do states, that have kaons. So then, this is a collaboration with many people, Molina, Feijóo, Liang, Dai, Roca, Martinez, and Kanchan Kemchandani. And I'll talk a little bit about, how we can get the interaction, for this meson interaction. And then, I'll talk about this Decay bar, the H0 2900, then the TCC, and then extrapolations, to higher states. So, okay, I have the pleasure to talk about something, that, many people know, not everyone. And it is the fact, the equivalence between the chiral Lagrangians and what's called the local, the Bandeau, local hidden gauge theory. Bandeau and collaborators made a nice theory for the interaction of vector mesons with themselves, with pseudoscalars, with baryons, everything. And for example, we have here, and then it says that when you have the interaction of vector, for example, pseudoscalar, this is due to the exchange of vector mesons. So the interaction in this theory is just given by the exchange of vector mesons. So here you have this vertex, you have this vertex. This vertex everyone knows. This is the typical vector going to two pseudoscalars, this thing, okay? And the other one is less known, that's the vertex that contains three vectors, and it's very little similar, but you have this thing. So give me 1 minute, to explain something here. When you have a Lagrangian and three vectors, this could be a mess. In fact, some people make a mess of it. But because you don't know which one of these three vectors is this one, you have so many possible combinations. Things might become horrible. However, one can simplify, and I like making things simple. Going to the limit you have, close to threshold, where the momenta, the three momenta of the external mesons is very small. So I'll go to this limit, which is close to threshold. So this limit means, that K of M is very small. K is the three momentum. So look then, at the polarizations, polarization vectors of the vector mesons. They are this epsilon1, epsilon2, epsilon3, and the third component in this limit is always zero. So the first component, the zero component is always zero. So then epsilon 0 will be 0 for all the external vectors. Very good. So then I prove by reduction to the absurd that this cannot be an external meson, cannot be an external vector. Because if it was an external vector, nu would be 0. I just finished it, I've shown it here. So nu would be 0. So then nu, then nu can only be, nu equals 0 would be 0. So it can only be nu equal 1, 2, 3. The component must be, special. And if the component there is special, then I have here the three vector, the derivative with respect to 1, 2, 3, and then this gives me the three vector, but the three vector is 0. So then this cannot be external, it has to be the internal one. Can be necessarily, has to be this one, in that limit. And that simplifies terribly, the solution. Because right now I can have there, I combine the two diagrams, and I have here the first vertex, and I have here the second vertex, and this one is the one that's contracted. This one and this one is the one that's contracted. Here you have the contraction, and then I make, Q square going to 0, and this is also going to 0 because, we are close to threshold. And then you get, this Lagrangian here, and this Lagrangian here is exactly the chiral Lagrangian that is given in this paper by Mike Burrs in Physics. So you see, I have proved to you now, and I wanted to do that the local hidden gauge, is more, general, but, in the limit of a small momenta, it gives you the chiral Lagrangians. So then, because it's more general, that's what I'm going to do to go. This, of course, local hidden gauge has been done, for SU3. So I will extend that, to the charm sector. I extend not the chirals, because we have bigger masses. I exchange the local heat engaged approach to higher mesons and higher mass mesons, and I exchange vector mesons like, Bando, Lady Bando tells me to do. So fine. Then, okay, we go ahead, and then I have the pleasure, and it was a surprise to me, that 10 years ago, 12 years ago, 2012, Molina and Tania Brands, did a work, and at that time we did that because we had to do something. I didn't have the slightest idea that one day, this could be seen. But then we made, the interaction of this star, K star bar. This, you see, this is certainly a state, exotic, because it contains, it's exotic because it contains, I didn't put it here. It contains, D and C, C and S, so it cannot be QQ bar. It contains an open charm and an open, strange quarks. So, it is exotic. So fine, to do the interaction, then we have the diagram that we had before, but with vector here, and exchange a vector meson. But the Bagdo theory also tells us that there is a contact term. So we take also into account the contact term. And then, in principle, one has a complicated amplitude here because there are 1, 2, 3, 4 vectors there, and you have 4 polarization vectors. But, things can be very simplified, by taking into account the projections on the 3 possible spins that we have. Spin 0, spin 1, and spin 2, when you have 2 vectors. So, these are the projectors, and then, it is very easy to separate the amplitudes into the 3 channels. So, fine. Then you see, I want to show you now, results there. What I want to show you is that we have this amplitude, this state, the amplitude of that going to that. In spin 0, 1, and 2, this is the contact term, this is the vector exchange, and this is calculated at threshold, the sum of the 2. So you see 1, 2, 3, and the 3 of them, the potential is negative. Negative means attraction for me. Okay? So then, the question is, will I get, some bound state? The answer I can tell you now is yes. This, is negative and is enough to bind. So we get bound states at that for spin 0, spin 1, and spin 2. But and this is with isospin 0. If I do that with isospin 1, all of them are repulsive. Nothing. In isospin 1, I will get nothing. I know that already from the beginning. So then I continue, and then this is only the potential. We have to unitarize, by putting that as a kernel of the Riemann-Schwinger equation or Bethe-Salpeter, whichever you want to call. And then, G is just the loop function of 2 meson propagators, which you have to regularize, by cutoff, or, dimensional regularization like it has been done in the previous talk. Fine, no problem. And of course, we also, the ladies were hardworking, and then they took into account also the decay width of this star, K star bar, going to decay, which is nice because that is the channel where they have observed, LHCb observed that in that channel, in the KD, KD bar, DK bar, channel. So we already had done that at that time. Fine, and then look, at that time, 12 years ago, these were the predictions. We predicted that for 0 plus, there was state with mass 2,848. This is the regulator, for the box here, right? And it regulates a little bit the width, with natural numbers. And these were, predictions for the other states, 1 plus and 2 plus. So, okay, 12 years ago, that was predicted. And now, the LHC collaboration, P collaboration finds, the X0, 2,166 with that mass, and a width 57. Look at that, the range that we calculated, and the mass, which is only, 15 MeV away. That was a prediction done 12 years ago. So, fine, then we continue, and then, Raquel Molina and I, we decided that because, there were tiny differences between that and that, we could take the data, and that's what one has to do, take the data to do fine-tuning, only fine-tuning, a little bit of the parameters to get exactly what the experimentalists get. So we did a little bit of fine-tuning, we wrote that paper, and on top of that, we also calculated a width, an extra width going to this star K-bar, which is a channel we had not done before. Because the 1 plus state only decays to that channel. So and then these are now, what we get. The thing below, is exactly experiment because we have done this fine tuning. That's fine. And there are the predictions there for spin 0, spin 1, and spin 2, which have not been measured. So we make predictions, very precise predictions, that's the predictions, for the mass the states should have and the width they should have, both. So now, to help, there are some experimentalists around here, Bell experimentalists, and we have done, they have observed so far, the zero, right? The zero state is the one that has been observed. The 1 plus, the 2 plus that we predict as a necessary consequence, these have not been observed. And we are, we are clear cut, that this state should be seen. This state exists. So, and then we want to help the experimentalists, and we suggest these reactions. Take note, experimentalists here, that we suggest these reactions and we calculate, the signal and the background, this is with the blessings of demanding referees, demanding on the background, so we did all the calculations required, and the message is that the signal of a background, is clearly seen. So in these reactions, we predict that this 1 plus state should be clearly seen. 2 reactions, okay? Take note. Okay, and then, we have continued, the work. I want to mention that in this work of Tanya Brands and Molina, we also, studied, it was just, we had to do something. So, we did the D star, also exotic. So we could have done the D star, D, and then we would have done the TCC, but it is irrelevant because the interaction is the same. So then, let's say, that we predicted that should be this TCC state already 12 years ago. So, and okay, and fine, and then now, we have done now in collaboration, with Albert Feijó, and we have done there the TCC, the interaction of the D star D, okay? And then, this is the experiment of the certain experiment with this mass and width, 400 keV, width, and this I'll come back to that, because, we do the interaction here, and then we find, as I have told you before, we can exchange psi or we can exchange rho, and then we get the interaction, which is this thing. Look at that. This interaction in these 2 coupled channels, the diagonal, fine, sorry. You give me 1 minute for being the first speaker? 1 more minute, okay. So anyway, this interaction is, very small, but because we have coupled channels, then you diagonalize that and you find, that this combination, has an attractive interaction. This combination has repulsive interaction. But the combinations happen to be isospin 0 and isospin 1. So automatically what we get is isospin 0, we get binding. In isospin 1, we get repulsion and we don't get anything. And it was funny, because, we predicted there, a width of 80 MeV, not the 400, the experiment gave. We said, no, we get 80 MeV and nothing. But then Michasenko, did a reanalysis of the data and found that taking into account, the spectral resolution, then, the width was much smaller. So, then when we adjusted, he also found the state a little bit more bound. When we adjusted to his, binding, then, we found a width 40 MeV. 40 MeV, which is exactly what Michasenko has done in the reanalysis. But it was done before his reanalysis. So, and I will work in 1 minute. 1 minute, and I finish.
0 minutes.
0 minutes? Okay, 0 minutes. Okay, then 0 minutes, I go to the conclusions. And I go to the conclusions. Sorry, I have many more things. But I explain myself. Okay, I explain myself with things, and that's the last thing I will say, okay? For Tanida, Tanida-san, we have there, the DD star, but this star S, we get, repulsive interaction, so we get nothing, okay? And that's why I said, I mean, that you should not see anything. And the time is over and I finish. Sorry. I mean, I had more things to say, but I mean, time is time. Okay? Thank you very much.
Thank you very much for your talk. Okay, question and comments? You can talk 1 more minute. What? You can talk 1 more minute.
I can talk 1 more minute?
One more.
Oh, very good, yeah. Oh, great. So I don't know where to begin. Yes, I want to begin here. You see, I mean, for Tanida, I mean here, for you. You see here, I mean, DS, here DS. We get DS, which is what you wanted to measure. We get their repulsive interaction. You see, repulsive interaction. So we get nothing here. And then the last minute, I will take only half. I mean, the only half minute is that we do the predictions now for the bees, for bees. And for the bees, I mean, BB, B star, BB, etc., B star. We make predictions and we find that it's more bound. Actually, Okasan also found, I mean, that in his model that was also more bound. So this is general. Bees get more bound than the bees in whatever model you use. And then in this, I mean, thing, and this is really, I mean, the final thing, this the predictions that we do for the bees. B star B, here, I mean, we predict states only for 1+, only for 1+. And then we have B star B, I mean, with isospin 0, we get 21 MeV. You know, now we have MeV. Before we had KeV binding. Now it's MeV. The minute is over. And then that's it. And we get more binding, and also the widths are also bigger, except, I mean, some which can only decay, I mean, for the B decaying into B star, we decay into B gamma. So then the widths are very small, KeV, again, or electron volts.
One short question? Giri.
I have a question. What's on the slide 24 and 25, please? What's on the slide 24 and 25? I haven't seen it. So please continue. 24 and continue speaking, please. Thank you.
No.
No.
Okay. Satisfied? May not be satisfied, but we have to stop. Okay, let's thank the speaker again. Okay, the last speaker of this session is on site, and Thomas Jude. He will talk about the Be Good experiment at ELSA. Okay.
Sorry, I thought there was somebody before me. I thought there was someone before me. No, that's fine. I didn't realize I was next. Right. Okay, thank you. Good afternoon, everyone. Yes, so today presenting strangeness photo production results from the Be Good experiment, which is a Bremsstrahlung photon beam at the ELSA Electron Accelerator in Bonn, in Germany. And so I called this exotic structures, namely in the sense that we can probe very forward angles for mesons and charged particles, leaving residual baryons of very low momentum exchange. And so we're susceptible to identify, for example, or in a reaction see extended molecular-like structure potentially. And this is probably important in for example, if you look at the M-star spectroscopy as motivation, these constituent quark models of 3 constituent quarks in a mutually generated potential fail to describe what we've observed experimentally, and this is in spite of seeing now a wealth of photoproduction data from numerous final states. And so the question is, what is the relevant degrees of freedom? Is this correct, or should we be looking, for example, at diquark-like structures, or extended molecular-like states, meson baryon degrees of freedom? This is particular prescience at the moment because very recently now it's like a paradigm shift in charm sector, in many pentaquark states and XYZ states, and there's evidence that we see, for example, molecular-like structure in the stranger sector. So archetypal evidence, for example, the lambda 1405. I will skip over this slide because this community is very aware of the structure, for example, the lambda 1405. But one other example for motivation is recent data and photo production of K0 sigma plus from the crystal barrel CBLSA TAPS experiment, where they see a cusp-like structure in the cross-section here at the K-star thresholds, and two thresholds labeled here. And it was argued at the time that this could be a off-shell production of K-star, which then rescatters to produce your K0 sigma plus in the final state. And namely, if this could be a dynamically generated state in this central region here, which is then lost as you go over threshold. And very interestingly, essentially, the only model that predicted the pentaquark states prior to their discovery, described them as a molecular-like system, an equivalent model was able to describe this as a destructive interference of two dynamically generated N stars, resulting in this drop cusp-like structure. So it could be considered like the strange cousins of the pentaquark system, if you like. And as we'll show later, this model also predicted that we would see constructive interference for the reactions off of the neutron, so acting almost like a smoking gun, that we see a similar mechanism maybe in strangeness photo production. And so just to sort of highlight here, a lot of details, but essentially this is a table with charm sector on the left, strange on the right. And for example, the pentaquark states and these proposed N-star states, both residing at very close to thresholds and with similar quantum numbers here. And so if you want to identify a molecular loosely bound system, for example, in photo production, we need very forward acceptance. For example, if you looked at this reaction here, K-on going forwards. And we need good identification of neutral particles, namely the identification of neutral mesons decaying to photons, almost isotropically. So for example, lambda 1405. And we believe this is what the Be Good experiment can offer to the community. So this is published, technical paper here, detailed write-up. Picture here of the experiment where we have the electron beam from ELSA, from the right-hand side here, impinging on a thin metal radiator to produce a Bremsstrahlung photon beam that is momentum analyzed event by event. This is amorphous or crystal radiator for linear polarized beams. And then the experiment is essentially two parts. We have a central calorimeter for crystals, ideal for neutral meson reconstruction, with charged particle veto detectors as well. And at forward angles, this forward spectrometer of tracking detectors, open dipole magnets, and time of flight rules for charged particle identification and meson and momentum reconstruction. On the left, zoom in on the central region, and here's the invariant mass of numerous mesons, plotted 2-photon mass here with nice time resolution for clean identification. Picture here of our tracking detectors, MoMA and Sci-Fi, and then a series of drift chambers here, tracking particles to the open dipole magnets. And we can identify particles via the momentum and beta. So protons, K+, pi+, for example. And given the shortness of this, just checking the clock's going down and not upwards. Given the shortness of this talk, I'm going to focus just on our results. So this is the last analysis or example of what we can identify in our detector. So just if I was to select, for example, K+ via the mass reconstruction, this is the missing mass, and you see different hyperons reconstructed from going forward, going K+. And couple this with our calorimeter to identify, for example, pi zeros, we can start to disentangle the almost mass degenerate states here, for example. And so this gives us very, very forward acceptance, which is unachievable at other similar facilities in this mass, in this energy range. So, as we mentioned there, very brief motivation that there was this potentially smoking gun signal in neutral kaon production, where maybe we see or not see these N-star dynamically generated states, which could be considered the partners of pentaquarks, for example. This was studied by one of our PhD students, Katrin, in this photo production of the K0 sigma 0 of the neutron, identified by the 2 neutral pion decay and the full reconstruction of the sigma 0. And our data are in the black and red. There's just different fitting techniques, essentially, compared to previous data from the A2 collaboration in blue. And essentially, you see the statistics are limited, but at forward angles, we have imposed on here this prediction for the total cross-section from Engels and Hulel, where we would argue at least we are consistent in shape and structure with this. And so this is now on the archive. We're not arguing that we see this state for sure, but at least we're consistent with this. And now we have more data, we'll be able to reduce this statistics by a factor of 1/2 at least, and be able to sort of give a more quantitative argument about what we're observing in this forward angle here. But at least it's consistent and of interest at the moment. Georg, another student, finished his PhD recently, and he looked into the photo production of lambda 1405 via the neutral sigma 0 pi 0 decay, which is ideal for us as we don't have background from the sigma 1385 to the same final state. And this is done with a complete kinematic fit, identifying the full final state particles. On the left, this is the invariant mass here, with our data in black, which gives good agreement with previous data, the class and Anki data here, for example. And tentatively, we argue that maybe there is a sort of two-peak structure that could be observed, as predicted from these chiral perturbation theory models here. And at forward angles, as plotted here, now sort of forward region here, so theta greater than 0.686, maybe we tentatively see a change in strength of this sort of two-pole structure if it exists, but it's very close to our resolution here. But what I want to focus on for this, it's not just this nice line shape, but this is the differential cross-section with respect to the beam energy, or W here. As there was a calculation that predicted this triangle singularity, which really drives the photo production of lambda 1405. And so this is exactly the same resonance that was suggested for dynamically generated resonance for this cusp in the K0 sigma plus state. And so this would drive this triangle singularity, and therefore would have to be close in mass to the K star sigma summed mass, and so again supports this idea of a molecular component, and then drives this lambda 1405 photo production until the kinematic conditions are lost, and then we see this drop in the cross-section. And the model prediction in purple was fitted to the existing class data of the time, which is this red data points. And now you see our data points in black, which is not a fit, this is just what we measured, but we get a very nice agreement here. We see this sort of drop exactly where it's sort of predicted. And so this, in combination with our data from K0 sigma plus, K0 sigma 0, would argue would quite interesting and evidence that maybe we are observing this dynamically generated states in this strangeness sector. We also have data for the ground state hyperons. So forward K plus lambda photo production, for example, very, very low T, so constraints on hypernuclear electroproduction, where it's almost a real photon here. And this forward angle is sensitive to high spin n star states, for example, where the Legendre polynomials change quickly over these regions. And you can see our data in black, very small, well, very high statistical precision compared to previous data in JLab and Sapphire. So we're confident this is a huge boost in support for isobar models, for example, in partial wave analysis, which needs this accurate description of forward angles here. And we also have this very high angular resolution, so we can bin in very small bins. Equivalently, we have the data for K plus sigma 0, and this really shows the benefit of these very forward angles where the momentum dependence changes very, very quickly. So our data again are in black with high statistics and this drop. We notice this like drop here, that's the K plus, K minus threshold of the proton here. Whereas previously it was noticed maybe a slight peak-like structure where there was disagreement between different partial wave analyses of contributing resonances here. But we can scan over this forward region, and if we do this, we can then extrapolate to minimum T, so when the kaon's going exactly forwards. And we have this cross-section here. So now this drop, or cusp, whatever you might want to call it, it's now a factor of sort of 3/4 loss in the strength of the cross-section. And plotted here are various predictions, such as the K bar proton bound state or phi n bound states with their predicted widths from these references here. And also we note the other cross-sections of others rising at this point. And so we have no conclusive argument or interpretation of this, but it's interesting to note that we're exactly at these thresholds and bound systems here. And there is indeed observed like this sort of smooth transition between these different states, almost as if we have some conserved S bar pair production at this point. And yes, this is also, we're now looking into this with K minus sigma 0, as if there's some sort of SS bar universality that we can observe. Okay, so with just over a minute left, this is just a very quick review of the work we're working on right now and what's coming out to publish. Well, we can probe this potentially molecular-like structure in the UDS sector. And given that we have this forward regional access for K plus production, for example, we're complementary to class data, and we can get to very, very, very low momentum exchange, so very low T. And we believe there is evidence of potentially this dynamically generated states observed both in the K0 production and lambda 1405. And I'll leave you with one just so what is next? We also have a lot of analysis going on in the non-strange sector, so we're taking more data in strangeness this year, ongoing. In the non-strange sector, we also have interesting results for the coherent production for 2π0 photoproduction of the deuteron. This is a bit out of context of what we're presenting here, so I didn't really show it, but it was accepted yesterday, and maybe or maybe not, this is a channel where we could observe these D-star 2380s, for example, in the UD sector. And so, thank you for listening. I'll leave it there.
Thank you very much for a nice talk. Okay, this talk is open for questions and comments. Okay, you're here.
This thing, I mean, that you show the triangle singularity, I mean, of meta-target ANWA. That's quite interesting, and I had lots of discussion with them, and I think they are right. The only thing is it's very difficult to calculate. I mean, because it has input, I mean, that it is not known. And it's not known experimentally nor theoretically. But so then, I mean, the strength that you put there, this is put by hand.
So it's a little bit muffled.
The strength, yeah, the acoustic is very bad here, I'm sorry. When I am there, I also suffer it. But the strength of the peak that you put there for the triangle singularity, right, this is the green thing before. I mean, the green thing, the other slide. No, next, this one, the green thing, triangle singularity component. This has been put by hand. It's not a result of any calculation.
No, this is your...
What?
This is the absolute...
No one knows how to calculate that.
Just
The green one. The green.
The green, no, it's not. It's
The green one, I mean, the strength, the position, yes, position is correct. The strength.
No,
the strength.
It's from the paper.
What?
It's from this
No, that's a paper, yeah, but I mean, the strength, I mean, you have to put by hand because no one knows how to calculate that, yeah.
Okay.
I mean, they asked me to calculate it, and I said, I cannot, but I know the market, and no one can calculate that so far.
Okay.
So the strength has been put by hand.
Yes, yeah, sorry, it's not from us, but from the original publication.
I have a short question on page 9. You say gamma neutron reaction.
Yes.
How do you prepare a neutron target?
It's a deuteron target.
Okay.
And then we do the same analysis with a proton target and subtract it.
Okay.
And there's negligible K0 sigma plus in the neutron.
For high energy gamma, probably.
So it's complicated analysis, and it takes a lot of data because we need to subtract the same amount of proton data, essentially.
Other question, comments? Okay, 1, 2.
It's just of curiosity. You showed the missing mass at the beginning, and it looked like the lambda 1520. So what is your resolution?
In these plots, so the resolution here is dominated by our, just for reference, it's dominated by our tagger energy, which is typically 10 to 15 MeV. The resolution here is of the order of probably 10 to 20 MeV in sigma, I think. We have actually, for the lambda 1405, I can tell you, we have it, this is for the lambda 1405, this is our mass resolution. Okay. So it would be similar.
Thank you.
I would ask, what do you mean by cusp? in order to say it's cusp, there must be a jump in the scattering amplitude, derivative of scattering amplitude. Where is it?
Maybe I'd prefer to rephrase it and call it a cusp-like structure. In the sense that I observe something that looks like it drops off.
Okay, it's not exactly the cusp, maybe not exactly the cusp. Okay.
Yeah, sorry, I'd rather just in terms of visually it looks like a cusp-like structure. But
Okay, let's stop the session here. Okay, let's thank the speaker again. And let's thank all the speakers again. And I was very sorry that I was late for 3-4 minutes.